just before starting, some announcements. The first of all is that the weather forecast announced that today will be the hottest day of the month in Rio de Janeiro, so drink water. So be 39 degrees. The second announcement is that it was supposed to have Sergio Muniz, but due to some problems with his computer, we swapped Sergio and Gabriel. Then the tutorial today in the morning going to be the Gabriel Landi from University of Rochester, starting the morning session. Please, Gabriel, the floor is yours.
Okay. Good morning, everyone. Thank you very much for being here in the morning. It's a pleasure for me to be able to come here to Rio and present some of the things we've been doing over in my group in Rochester. So to kind of motivate the talk, I wanted to use this experiment here. So this was done in the group of Simone Gasparinetti in Sweden. And what they do there is they implement a autonomous absorption refrigerator using three superconducting circuits. So what you see here are 3 qubits, red, blue, and green. And essentially, the goal is to cool green, right? So green is maybe your work qubit, is the thing that you're using to do quantum computations or whatever. And every once in a while, you want to make sure that you can cool green as close as possible to the ground state. And so they did this using this idea of an absorption refrigerator. So the setup is a little bit like this. You have a hot and a cold bath. And of course, from thermodynamics, we know that heat wants to flow from hot to cold. That would be the natural direction of heat flow. However, things here are engineered such that there's a resonance game being played here, such that because the interaction is weak, and this qubit is very far off resonance from this qubit, the flow in this direction is actually suppressed, unless there is an excitation in this qubit. So it becomes a kind of a 3-body interaction where 2 excitations here in red and green, they are kind of combined and become an excitation in cold, which then is sucked into the cold bath, right? So that's the idea. So this is the hot and the cold bath are just kind of lying there. And then every time you want to cool your green qubit, you just make sure to populate the hot qubit as much as you can. And every time the hot qubit is going to flow excitations in here, is going to suck an excitation out of the green qubit. That's kind of the idea, right? So this is a little bit of cooling on demand. You can imagine that this qubit is doing whatever. I kind of put this in a little bit of a kind of a gray thing here. You don't really know what this is. You don't really care. This is whatever, your computation. But what you know is that every once in a while, you want to reset your qubit. So you want to make sure that if there is an excitation in there, you suck it out. So now, in quantum thermo, we would usually describe this using steady state, right? We would say usually that there are 3 baths. This would be an actual bath, and we would talk about currents. So current from the hot bath, current from the cold bath, and so on. We would do a kind of a current balance, a heat current, and we would check if this actually is actually cooling because we're looking at average currents. But steady state is all an ensemble idea, right? This is like on average what current is flowing. What I want to introduce here, and I think this experiment motivates this very well, is this idea of, sometimes you don't want to look at this as steady state. You want to look at this as a single shot. Like, in the middle of your computation, say you want to reset your qubit, you just turn the whole thing on and remove an excitation. So it's never really a steady state. It's more a stochastic picture. Now, what is interesting about this, let's imagine for a second that this is like a classical picture where excitations can jump back and forth, here or here, right? And let's imagine that, that this picture holds, right? Then we can start to think about, what to expect from this kind of cooling process. For example, we can think about all the things that can go wrong before the cooling is actually successful. Imagine this, right? An excitation comes in here at time t equals 0. And now what you want to do is you want to have an excitation here, and then you want them to combine to become an excitation here, and then you want this excitation to be sucked into the cold bath. These are all stochastic events, right? It could be that they happen, it could be that they don't happen. So there are a lot of things that could go wrong before you can actually, extract this excitation, right? It could be, for example, that a hot excitation comes in here, but then before they can actually combine, this excitation goes back to the hot bath. That can happen, right? And then you have to wait a little bit more. Or it could be that maybe there are two excitations here. You're ready to go, but then an excitation comes in from the cold bath. That's more rare because the bath is cold, but it can still happen. And then you have to wait until this excitation leaves here before these two can combine, and so on. So there's an infinite number of things that can kind of go wrong before your cooling is actually successful. And now you can also ask kind of different questions, right? So while in steady state, we just think about currents and say entropy production, we can change the question now a little bit if you have this stochastic picture in mind. We can ask, for example, how long does it take to cool a qubit, right? Suppose I turn this on average, how long does it take to cool? Or we can talk about the full distribution of cooling times. What's the variance, what's the fluctuations of cooling times, and so on. We can ask about what are the fluctuations of entropy production within a single cooling event, right? Is it always the same entropy production? Can there be more entropy productions, and so on? So there's a lot of cool questions that we can ask if we think about this at this stochastic level. That's kind of my motivation. Just to give you an example, this is the experiment that they do. So the cold bath is always kind of turned on here. And then they simulate a hot bath by sending in noisy microwave radiation. So they, for a certain period of time, delta t, they just essentially make sure that they get some excitations into this hot bath. And then essentially they measure the population of this qubit. And you can see the curves here. So the curves are for different, essentially, temperatures of the hot bath as a function of how long you actually excited the hot bath. And the only important thing about this curve is that this dashed blue line down here is the temperature of the coldest environment in this entire system, right? So you're actually cooling below the coldest possible temperature in your device. So that's the goal. Okay. So then, yeah.
I'm not familiar with the experiment, but just to understand, in the steady state, is the qubit cooled correlated with the other two qubits? Is there a correlated 3-qubit state at the end?
There is no steady state, right? So this qubit is not really coupled to a bath.
Oh, okay.
They excite. I mean, it is in practice, but they don't really. I mean, this coupling to the bath in their case is pretty much isolated. So what they do is they excite this qubit in a kind of simulation way by applying a pi pulse. So then it simulates the idea that maybe an spurious excitation just kind of got in there.
Got it.
Okay, so this introduces this idea of stochastic quantum thermodynamics. And so I'll spend the first kind of third of the talk trying to motivate what is stochastic thermodynamics, because there's a fundamental problem here. We don't see quantum systems, right? No one in this room ever saw a quantum system, right? We see data. We get the lab and we measure, we get data, we get bit strings. And then what we want to do is, okay, so what can we say about a quantum system from data, right? And more interestingly, what can we say about thermodynamics from this kind of data? So I will be interested in this entire talk in this concept of a sequential measurement. This encompasses quantum jumps that Marcelo introduced yesterday. It also encompasses a broader class of processes. So the basic idea, I will always have in mind that for me, a measurement is essentially a interaction with an ancilla, right? And so in the usual setup, the one we learn in textbook quantum mechanics is there's a prepare and measure where you bring in a system prepared in some state. Then you bring in a probe, an ancilla. You make them interact. Now the probe has acquired some information about the system. You measure the probe, you get some data. And then you reset, right? So there's this line here. You completely reset the process and you repeat. That's the prepare and measure usual. This is what we learn in textbooks, right? Sequential measurements is you don't reset the system. So you bring in an ancilla, you measure the ancilla. Usually we can assume that we throw away this ancilla, right? We just throw it away after measurement and we bring in a fresh new one. And then we measure this ancilla again, but the system is never reset, right? Now, for those of you that have worked with collision models, this is a collision model, of course, right? There's only one small caveat, which is that here it's a continuously measured collision model because we're measuring the ancillas at each step, where in collision models, we don't necessarily measure the ancillas. Now, let me give you a very simple example. Suppose you have a qubit. Suppose you apply a unitary, and then you measure in the computational basis, right? So that's the protocol. You apply some kind of unitary, local unitary in the qubit, and you measure in the computational basis. And you can design an ancilla that will implement this kind of operation. So here will be kind of the stochastic dynamics. You have a system that starts in some state psi 0. You then sample the first data point from this distribution that the system transitions because of the unitary from psi 0 to x1. And we use the update rule to say that if we actually observed x1, then we have to update the state of the system at step 1 to x1. And then we sample a second data point, x2. This is now a conditional probability that is quite important, right? Because this is the whole point of being sequential, right? It's like given the previous measurement, what is the probability that I obtain the second outcome? And so this is going to be given by this kind of sandwich here. And then we update the state of the system to x2. And so what you get in the end is a bit string of what I'm going to call emitted symbols, your data, right? Which is just a sequence of outcomes. And in this particular case, this will be described by a probability distribution that forms a Markov chain. This is because of the projective measurement nature of the process. So projective measurement is so strong that you completely reset the state at each step, and therefore you'd retain no previous memory. So the distribution at each kind of time step xn depends only on the previous one, right? So this is kind of interesting because now you obtain a correlated data set, right? So if you do sequential measurements, your data is not independent of each other. And I will try to emphasize this quite a bit because this leads to a lot of interesting things, right? For sequential continuous measurement, the data is always correlated. It's not like in the prepare and measure scenario where you have independent data points. You have to take into account this kind of correlation. Okay, we can generalize this a little bit. And this will actually lead to something that has a much larger memory than a Markov chain. For example, we can just apply a set of cross operators. The recipe is kind of the same. I don't really have to go through it in much detail. We prepare the system in some state row 0. Then we calculate the probability of observing the first symbol, and we update the state in this way. And then we keep going. But the important thing now is that the probability of getting the next outcome depends now, in principle at least, on the entire history, right? So as soon as you go to cross operators, then the memory becomes not Markov order 2 or 3, it becomes Markov order infinity, meaning it will depend, each data point, in principle at least, will depend on the entire data history. And so I wanted to emphasize the connection between these and the so-called hidden Markov models, right? So a hidden Markov model is something where you have a hidden layer that you never see, and then you have a visible layer, which are the emitted symbols, right? So this is exactly what's going on here. The system is evolving, right? But you never see the system. You see these symbols that are being emitted. This is your bit string. And then you have to ask the question, what can we learn about the quantum system from this sequence of emitted symbols? Okay. I will change notations now to introduce the idea of instruments that I have found to be really, really convenient. So I wanted to take a few minutes to just tell you a little bit how they work. So instead of working with cross operators, right, we can be a bit more general, and we can define an instrument, which is a super operator. For example, in the previous example that we had, the instrument applying the cross operator f rho f dagger, I'm going to call it M. Yeah, this is to the, let's say, 0th order in the expansion. This is just, I'm saving a few characters here, so I'm having to write things in a slightly more compact way. But instruments are very, very nice for a few reasons. First, this allows us to generalize the whole idea to inefficient measurements. So actually, every kind of open dynamics that you have can always be described by an instrument. So for example, you can bundle cross operators. You can say, maybe I have cross operators, but I don't have resolution. So I just kind of measure them and bundle the results in some way. Yeah, so that's one of the big advantages. And the other big advantage, as I hope I will illustrate in a second, is that they are very intuitive to manipulate and to marginalize. I'll explain what that means in a second. So an instrument is an object that encompasses this entire process, right? It contains information about the ancilla that you bring in, about the unitary, about the measurement that you do in the ancilla, and so on. It's a big object that essentially combines everything into a single kind of a super operator. Yeah. Okay. What I've shown you so far is what we usually call conditional dynamics, because it's the dynamics that the system is evolving stochastically, given that we know the data. We measure the ancillas, we know what outcomes we obtained. You can also have the unconditional dynamics, which is you can assume that you measure, but you don't really know the outcome, or you can assume that you just don't measure the ancilla. It doesn't matter, right? And so this will now be given by an instrument that is just a sum of the instruments. That's one of the reasons why instruments are convenient. You just, sum or marginalize over the instruments that you want. And this will now allows us to consider also the unconditional dynamics. This is the open dynamics, which takes into account the back action, right? Because the measurement step, because you're bringing in ancillas, you're perturbing the system. And so even if you don't measure the ancilla, you're still disturbing the system. And so the unconditional dynamics would take this into account. Okay, so I wanted to stress a little bit more the connection with hidden Markov models. So a hidden Markov model will usually look something like this. You have a state space, discrete set of configuration states, and the system can jump from one state to the other. So maybe it can jump from A to B, and every time it jumps, it emits a symbol, right? It emits some data. That's how you write down a hidden Markov model. The hidden Markov model is actually fully specified by this kind of probability distribution. This is the probability distribution that given that you start in sigma prime, that you jump to sigma, and at the same time that you emit some symbol x. Now, we can define an update rule a probability for different outcomes, and we can define an update rule. This is a Bayesian update, right? So we can say, I have a hidden Markov model. Suppose I observed as the symbol x = 1 being emitted. What can I say about my system, right? What have I learned? How can I update my probabilities about the system, given that I observed this kind of outcome? And so there's a Bayesian update rule. And if we write these things, you don't have to worry about kind of the mathematical details, but we can write these things in kind of convenient ways such that it looks exactly like the application of an instrument, right? So the formulas are formally analogous to the application of an instrument. So essentially, what I'm trying to say here is that this kind of sequential dynamics of quantum systems is pretty much a hidden Markov model. There's one fundamental difference, though, and that is that for hidden Markov models, these transition matrices that you can define from these probabilities like this, they are well defined as what they call substochastic matrices, whereas for quantum models, they are superoperators. And so that leads to that's where the quantum physics is, right? Is the fact that this is not a simple matrix with real entries, but these superoperators can be complex, they can have coherences, and all of that. So all of the quantumness is in that. But formally, the theory is almost identical to a hidden Markov model. Now, why do we care about this? And why am I talking about it? Well, one of the reasons is because if we can understand this kind of hidden Markov structure, we can make predictions about the future, right? So suppose we want to predict what's the next symbol that we're going to get, right? X of n plus 1. And I argued before that this will, in principle, depend on the entire history of outcomes, right? So the prediction is very complicated. However, if you know the state of the hidden layer, this probability is the same as this one. So you have compressed your data. Well, this can imagine n is 10 billion. This could be a huge bit string, and this could be a qubit, and you just have to start a 2x2 matrix. So it's that gigantic data compression because you make up essentially you're estimating the underlying hidden layer. So this is good for making future predictions, right? It's a tool that is used for making future predictions. One example that people are actually studying is, again, of course, in the classical context, not in the quantum, is using this for predicting, say, the hidden state of ChatGPT, right? So ChatGPT emits symbols. These are the words that come out of it. And then you can say, what's the hidden state of ChatGPT, given that I observed a certain set of symbols, or whatever, any large language model, right? So there's a lot of people kind of interested in this idea. That's one of the reasons why thinking about sequential continuous measurements is nice, because it allows you to make predictions about experiments. OK, so now I'm going to move to quantum jumps. So this is part of this tutorial paper that I put out with Mark, Michael, and Patrick, where we try to essentially combine essentially concepts that appear in quantum optics with concepts that appears in mesoscopic physics, and try to write a kind of a more unified way of sequential measurements that applies to both. So for quantum jumps, what we actually have is a Lindblad-Messer equation, which has some unitary Hamiltonian part and a set of jump operators. This is very similar to what Marcelo presented, right? And in fact, this part I could almost skip. The basic idea is that if you look at the infinitesimal evolution of this equation. So you integrate it. So this is the Liouvillean, right? The Liouvillean is the super operator that has all of this. If you integrate it for an infinitesimal time dt, you can write this as a sum of instruments. And there will be a set of jump instruments, which are essentially dt times the application of L rho L dagger. Yeah. And I will henceforth call this thing L rho L dagger. I'll call it J. Okay, so I will use this quite a bit. So J is the jump without the dt, right? And then there's also another instrument, which is the no jump instrument, which is kind of a smooth thing, right? This one is very dramatic because it's like a very strong change in the system. And this one is a smooth thing because it's like rho plus dt something, right? So it's like a small correction. And this L0 is now what's called the no jump superoperator, right? Which encompasses the unitary and also this correction term associated to the jumps. Yeah. So the basic idea is that the probabilities are always given by the trace of the instrument times rho. And for the jump instruments, this is proportional to dt. So actually, at each time step, the probability that you actually jump is infinitesimal. And so your dynamics might look something like this. It's most of the time a kind of a smooth dynamics, but every once in a while, you get a jump, right? That's the jump unraveling. There's one thing that I wanted to emphasize, which is it's kind of a technical thing, but really this, I mean, we've been thinking a lot about this because there's a lot of subtleties associated to it. There are two ensembles that you have to think about when you think about quantum jumps, and they're different, right? So we have what we call the T ensemble, where you say, I'm going to monitor my system for a finite time. And then the amount of jumps that happen in between is a random variable, right? It could be whatever. And this is what we just described. The instruments are essentially you jump or you no jump. And the data that you get, right, the outcomes, is essentially a bunch of zeros because most of the time you don't jump. And then every once in a while you get a jump, right? You could also operate at another ensemble called the N ensemble, where now you say, look, I'm going to monitor the system until N jumps happen. But then the time where the process ends is a random variable now. And in this case, we can define instruments, which are essentially an instrument associated to a time tau between jumps and an output x. And the instrument is just you evolve with no jump, and then you jump, right? And the trajectory now is strongly compressed. All you need to specify is a sequence of the jump channels. These are the x's, so what jump happened, and the interval between jumps, right? The tau between jumps, okay? So I like to think about this a little bit like, you know, Guitar Hero or something like this, where you play a video game that you have different symbols. The symbols are the emitted, are the x's, right? So it's like random symbols that are usually from a kind of a finite collection, a finite alphabet, right? So it could be, you know, 1, 2, or 3 kinds of jumps. And these jumps, so the symbols are random, and the time between them are also random. That's kind of the idea. Okay, we can also do something. This is, again, a very nice thing about this instrument business. So when we have this N ensemble, we have an instrument that has 2 symbols, right? The emitted symbol and the time. You could also play the game and ask, well, what if I don't care about the time? I just care about the order of these symbols. What have I emitted, right? It's very easy to do this. And that's, I guess, one of the things I love the most about working with instruments. You can just integrate this thing over tau. You just integrate over tau. You marginalize over tau because you don't care about this outcome. And then you get an instrument that is what we call quantum jumps with no time tags, right? It still has information about what channel jumped, but you don't care about when it jumped. And now your trajectory is just a sequence of symbols, right? So by playing this kind of game, it's very convenient. You can marginalize your instruments, and you can build simpler processes. So here's an example. Suppose you have a lattice, say fermions, spins, whatever. And suppose you play with a process which allows excitations to be exchanged from the left BEF to the system or from the system to the right BEF. So I allow these 2 processes. And I'm going to label these processes IL and ER, right? And now I want to ask, you know, what is the probability that I observe a certain sequence of emissions? So in this example, what we have is a particle is injected, then this particle starts moving around. Maybe it's like tunneling, you know, moving around in some complicated way. Then after some time, you see another injection. And then after some time, you see, you know, an extraction, right? And so an experimentalist with access only to this kind of process would only see 3 numbers, right? This is a very complicated dynamics, but all you would see is IL, IL, ER. That's your bit string. You see nothing else, right? And then you can ask, what can I learn about my system if this is the sequence that I observe, right? And this is an interesting question. For example, what can you learn about this system in particular if you observe 3 sequential injections, IL, IL, IL? Well, this is a lattice with 3 sides, so you know that the lattice is full, right? So you can learn something meaningful because you know that the lattice has 3 sides, so you know that it's full. If you observe 3 injections, the next one has to be an extraction, with certainty, right? That's the only possibility. So you can still make, you can still learn something about the system. Okay. The other thing that I wanted to mention, and this is also quite important, is that when we talk about quantum jumps, there are 2 ways in experiments that people actually detect them. I put a couple of examples here. This is an example where people detect what's called direct photo detection. This is quite similar to what Marcelo was presenting. This is some complicated semiconducting circuit that is emitting photons, and you just put a detector close to the system, and this detector clicks every once in a while, right? So in this case, the system is coupled to an environment. The environment is the electromagnetic field. And a quantum jump is a click in the environment, right? So you're monitoring the environment. And every time you see a click, you say, well, a quantum jump happened, okay? So this would be a direct detection of quantum jumps, right? You're actually seeing the quantum jumps from the perspective of the environment, right? Very often, especially in semiconducting physics, you don't really see the jumps from the perspective of the environment. You see them from the perspective of the system. So this is one paper that I particularly like. What they have here is a quantum dot. The dot is this dot here. And they introduce this thing called a quantum point contact, which is just a kind of a constriction, right? This is a kind of a conducting channel, but they put a little constriction here. So the current is kind of packed around here. And now, because every time there is an electron here, the current is going to feel the electric field from this electron. So the current that you measure here is going to change. And so this is the experimental data that they get, where they see essentially the current changing up and down. So this current is an indirect monitor of essentially the occupation of the dot. You're measuring a population, right? You measure the population of the dot, and you notice that the population of the dot changes abruptly. And now you can say, well, when it goes from here to here, then a quantum jump happened, right? But you're not actually detecting the quantum jumps from the perspective of the environment. You're detecting quantum jumps by measuring the population of the system. Yeah? Now, when you have quantum systems, you will usually have kind of a mixture of both. So here is perhaps the simplest model that you can play with that will display very nice behavior. Suppose you have a qubit with a Rabi drive, sigma x, and suppose that you monitor the population sigma z. So you monitor the population of the qubit. Now, the way you do this is through another kind of sequential measurement that I won't go into. It's called quantum diffusion unraveling, which is essentially the way that you describe continuously monitoring the population. But this is kind of what you obtain if you look at the population of the qubit, right? If the monitoring strength, this gamma is how strongly you monitor your qubit. If the monitoring strength is very strong, you see what's pretty much a classical up and down dynamic. You see pretty much quantum jumps, right? The system is just jumping up and down. But if gamma is very small, you actually see Rabi oscillation, right? So you can see, they're not the nicest Rabi oscillations, but they're still Rabi oscillations, right? So this kind of illustrates a little bit the interplay between actually having something that looks like quantum jumps or having something that is just quantum. Like here, I wouldn't say there was an actual jump, right? So this is something different. But for semiconducting quantum dots, you're very often in this kind of regime. And you can say that every time there's a jump up or a jump down, you can associate that to a click. Another very nice set of experiments people do with quantum dots is when they have a double dot, right? And usually they operate this kind of quantum dot in this Coulomb blockade regime, where essentially you're never allowed to have 2 electrons in the dot, in the system, because there's a lot of electrostatic repulsion. So essentially your Hilbert space is either the double dot is empty, or there's a dot at the left, or there's a dot at the right, right? And what they do here, this is kind of very common transport, is they have this kind of double dot coupled to one BEF here and one BEF here with different temperatures and chemical potentials. And they can actually measure essentially the population of these dots using a trick, which is to put this similar kind of quantum point contact, but they put it a little bit asymmetrical. Remember that the quantum point contact is a constriction in a current, which essentially feels electric fields from the dot, right? It feels when there's an electron there. Now you place it in a way that is asymmetrical, a little bit closer to the left, for example. And then the current is going to feel something more strong when it's kind of closer to, when there's an electron here, or feel something that is not that strong when there's an electron here. And this is actual experimental data. This is from Natalia Ares's group, and this is the current. And you see that it's pretty much a 3-level system, right? There are 3 configurations like this one. And essentially, the system spends some time in some state, then it jumps, then spends some time in another state, and then it jumps, and so on. You can even see these kind of peaks. This is a second electron trying to go in, but because of the Coulomb blockade, it just pulses back, right? So essentially, the system is effectively behaving like a 3-level system. And I think this example is very nice because there are quantum jumps happening here, and you're monitoring them indirectly. And you can now associate specific transformations in the system. There's a one-to-one mapping between a transition in the system and an event in the BEF. So for example, if I know that the system changed from 0 to L, meaning an electron entered the system, then I know that the BEF process that must have generated this is an injection on this side, right? There's a unique, it's not always like this. Sometimes there is no unique way of kind of mapping the kind of dynamics of the system to the dynamics of the BEF, but in this case, you can. Okay. So now I'm going to use some of these ideas to discuss essentially the operation of thermal machines. This was work done with my PhD student Abe and also with Patrick Potts. So I want to think a little bit more about this double dot system. And I want to go back to the basic idea of essentially thinking about this at the stochastic level, right? So now we have events. The events are essentially injection hot, extraction hot, injection cold, extraction cold. These are the events that can happen, right? And now I want to see, okay, what's the thermodynamics of this? If I can see these events, happening, what can I say about the thermodynamics? Well, we can see very easily, for example, that an event like TAC is pretty much the operation of a heat engine, right? Because this is heat that is flowing from hot to cold, right? And at the process, you extract some chemical work, right? If heat flows in the natural direction. An event like this must be essentially a cooling cycle, right? Because essentially, you're allowing heat to flow from cold to hot. And we know from thermodynamics that this comes at a cost. You need to spend work, right? So if you just observe this cycle, we know for sure that there was cooling. What is interesting, though, is that there are also what we call idle cycles or bounces, right? Because you can have a situation which is, the double dot is empty, electron comes in, bounces back, right? And same for the cold BEF. So you have hot bounces and cold bounces. And now the question that we want to ask is, if we only see this bit string of events, this is all we see, right? So that's our data. Can we identify individual cycles from this data? That's the question, right? Now, in general, if the system is not in the Coulomb blockade regime, if the system can have 2 excitations, then this is not possible. And I will explain to you why. This is an example of a substring that would be allowed if the system could have double excitations. Essentially, you inject in the cold, inject in the hot, extract in the hot, extract in the cold. Now, if we look at this like this, injection cold, extraction hot, that's pretty much a cooling cycle, right? Is this one. And injection hot, extraction cold is this one, right? So these would be essentially a cooling cycle and a heating cycle kind of staggered with each other. But this could also be injection cold and then extraction cold, which is a cold bounce, and injection hot, extraction hot, which is a hot bounce, right? So you can't really tell apart. If the game that you're trying to play is, what kind of cycles can we identify just from this kind of bit string? If you can have 2 electrons here, it turns out that you can't really do that. It's not possible to identify individual cycles. Now, what Abe proved is that actually having a single excitation, having a model that only allows for a single excitation is a necessary condition to be able to identify cycles. So we looked at Lindblad master equations that essentially only enabled for a single excitation at any given time. What we concluded is that the entire Hilbert space of the process has to be split in a block form. There's essentially what we call the post-injection subspace and the post-extraction subspace. Now, every time that an excitation comes in or out of the bath, the system has to move from one subspace to another subspace. There's still a lot of really cool physics that can happen within each subspace. The system could extract work, consume work, and so on by just moving around within the subspace. That's fine. But every time there is interaction with the hot and the cold bath, it has to move from the hot to the cold subspace. This is a necessary condition for us to be able to identify individual cycles. And the Coulomb double quantum dot in the Coulomb blockade is a good example of this. So what is really nice about this subset of problems is that we can now go from a bit string of jumps to a bit string of cycles. So we're going to define 4 cycles. We're not very creative, so we call them 1, 2, 3, and 4. But essentially, we can bundle, and we can see, because there can only be a single excitation, you never observe 2 injections, 2 extractions. So x equal 1 is what's called the engine cycle. X equal 2 is the cooling cycle. X equal 3 and X equal 4 are the bounces, right? They are the idle cycles, the cycles that are kind of silly, nothing interesting happens, right? And once we do this, I mean, from the perspective of instruments, again, it is very convenient to do that. We just need to bundle the instruments together. So, remember that these products like J e to the L0 was the instrument for a single jump event. We can just bundle 2 of them now and have, J injection followed by a no jump. Then you wait a little bit longer and you have an extraction. We integrate over this kind of intermediate variable, and we can build the instruments associated to cycles. So we can, using this idea of instruments, we can go from stochastic dynamics of jumps to a stochastic dynamics of cycles. That's a nice feature. Yeah, and this opens up very nice questions. For example, the basic ones is what's the probability that a given cycle is of a given type, right? How often does it happen to be, does a machine operate as an engine? How often does it operate as a refrigerator? How often does it just bounce, right? Or how long do these cycles take? On average, how long is a cooling cycle versus a heating cycle and so on? So we can ask a bunch of stochastic questions, which are quite interesting. Yeah, I'm going to kind of skip the math here a little bit. I just wanted to point out that once we have this kind of instrument for the cycle, if we marginalize over time, we can get the instrument for the cycle type. So now we have 4 symbols, 1, 2, 3, 4. And this is the instrument saying, which cycle can happen. So this little object here is the probability that you observe a cycle of each type. And I'm going to kind of skip the details about what's the correct choice of state. We can discuss this later if someone is interested. Now, this object is interesting because it connects to steady state. So this is one of the connections between the steady state picture, where you just have currents, and this kind of stochastic picture, where you have individual cycles happening, right? What this says is that the heat current flowing through the model, or the excitation current, is essentially the difference between engine cycles and cooling cycles divided by the time between cycles. This kind of makes sense, right? So you can have a cycle that goes this way, a cycle that goes this way. The average current is just the difference in probabilities divided by the average time, which I think is pretty cool. We can talk about correlations between cycles as well. That is kind of neat. So for example, we can think about cycle bunching and cycle anti-bunching. If you observe an engine happening, what's the probability that the next cycle is also going to be an engine, or maybe it's going to be a refrigerator, and so on. So we can play games about cycle correlations. And here is some concrete example for a 3-level system. Now, when I think about a 3-level system, I usually think about the double dot. But of course, it's equivalent if you think about this Scoville, Schul-Dubois kind of engine. You just have 3 dots here. We call them 0, 1, and 2. The hot bath, it causes transitions between levels 0 and 2. The cold bath between 2 and 1. And then you have a kind of coherent work extraction between levels 1 and 0. So in the 3-level maser, this would be, just say emitting or absorbing a photon from a cavity, for instance. So this is, for example, the probabilities that a cycle is of a given type and it takes a time tau. So this is a waiting time distribution, but it's a waiting time distribution filtered by cycle. It's like how long does each cycle take given the cycle type. You see it's not too different in terms of kind of structure. You also see these kind of wiggles here, and this is very characteristic of the coherent property. So when you see wiggles in the waiting time distribution, this is because this is a unitary kind of transition. This one is a little bit more interesting. This is the probability of each cycle happening, right? And this is as a function of temperature ratio. So we chose things here in a way that here the system on average operates as a refrigerator, and here on average it operates as a cycle. So you see that in the refrigerator regime, actually the most likely event is just a cold bounce. It's x = 4, which is just something comes in from the cold bath, just bounces back. That's the most likely event. The second most likely is the actual refrigeration event. That makes sense. And then you have the engine cycle and the bounce, hot bounce events. And then as soon as you cross this point, things invert. Yeah? We can compute also conditional times. So this is the average time of a cycle, given that the cycle was of a type 1, 2, 3, 4. And we can now use these quantities to build the notion of intermittency. So this is something we're just now starting to explore. Intermittency is pretty much, how often is your machine actually not doing anything useful, right? Now, in steady state configurations, we usually think about these things in terms of current fluctuations. And I will talk a little bit about this in a second. But here we can think about fluctuations at the level of individual cycles. Pretty much, the idle cycles 3 and 4 are useless, right? It's just bounces, nothing happens. Whereas 1 and 2 is actually something meaningful happening. It's a cycle that either you cool or you refrigerate. So here is we plot the ratio. So this is average n. And this turns out to be the average number of useless cycles between two useful cycles. So a useful cycle happens, and then there's a bunch of useless stuff, and then a useful cycle happens again. The average is given by this ratio. We show that. And this one is essentially the average time between two useful cycles, right? It's, which we plot here in blue. This is essentially that's kind of the idea. So for example, what we see is that the average number of useless cycles between useful ones is kind of symmetric between the two regimes, but the time is very different, right? The times are much shorter in the engine regime. So times tend to be a lot faster, whereas in the cooling regime, everything kind of freezes down because you're operating essentially at lower temperatures. Okay. No. Wait. Oh, there we go. Okay, so I will not have time to go through this, but that's great because Guilherme, who is here, is going to present a poster this afternoon, and so I won't have to spoil the fun from him. But essentially, we extended this idea of cycles to what we call thermodynamic excursions, right? So the basic idea, I'll just kind of flesh out the details, is that we can imagine a process where the system is jumping between a bunch of configurations, right? And we can establish two configurations, or two regions. We call them region A, region B. And we can ask a question about excursions to region B. So we can say, suppose the system starts here, and an excursion starts as soon as the system jumps to region B. And then the system is going to jump around here for some time, and then eventually go back to A. And then we call that an excursion. So the system starts in A, it does an excursion through B, and comes back. And what we've been looking at is essentially how to compute currents and what we call more generally these counting observables within excursions, right? So that's kind of the idea, but I'm not really going to spoil any of this fun. And so I'll just stop here and say that what I find interesting is that sequential quantum measurements give you a time series, right? It's a classical time series. Data is always classical, but it's highly correlated. And it's correlated because of the quantum properties of the quantum system. We can do Bayesian inference. We can update our knowledge about the state of the system given these outcomes. And we can also use this to try to ask questions about the thermodynamics, right? What can we learn about thermodynamics given this time series of data? What we're still working on is to kind of improve on this idea of machine intermittency, which I find really cool. And also the work on stochastic excursions is still so far completely classical, but we are very excited about it, but it's also unpublished. So that's pretty much all I had to say. Thank you very much.
Thank you very much, Gabriel. Some questions now? Some questions?
Gabriel, very interesting. I have a simple question. In one of your last biograph, you were showing the probability for the machine, for a certain type of machine for the various cycles, exactly, the second one. And then I got confused because I thought you were identifying the type of cycle with the machine. I mean, you were showing hopping and so on, but there in the second one, you're showing that, and also in the other, that each cycle can also be a different machine. So I got confused in that.
No, sorry. Yeah. So, I mean, so all cycles can always happen, right? So for any kind of parameter regime, all cycles can happen. It's just that some of them are more likely than others. So in what we call the steady state cooling regime, so this would be like refrigerator at the steady state sense, you know, if you look at the average current, what we can actually have happens is that it's more likely to observe the machine cooling than it is to observe it heating.
Okay.
But
it's not a single cycle. This is a steady state. So this is an average over...
So these curves are the probability that individual cycles happen. So kind of coming back to this picture, you know, what's the probability that if you're monitoring this, you observe tack, tack? And actually, there's a nice, you know, if you look at this kind of data, right, essentially you can associate that with specific jumps. Say, for example, from 0 up to this level and then down. That's one specific cycle. But you can also have, in principle, other cycles. Like, for example, you can have, let's see if I can find one. Yeah, like here. You see, it goes from 0 to this kind of intermediate peak.
Yeah, no, it makes sense. It makes sense. I mean, yeah. Okay, thank you.
Okay, so in principle, you can define the same for cycles also for a generic number of dots, even one or n. So you just say it goes through one way, the other way, or just have some excursion. And the probability will depend on n. Did you compute how this will change with n?
Absolutely. But again, the idea only works if you're in the Coulomb blockade regime. So only one electron per dot. But yeah, then it's super easy, actually. I mean, it's the
change with n, because I guess the probabilities will be modified by n.
No, absolutely. We didn't look into that. But that's something we probably should. Yeah.
However, I understood that if you have more than 3 level systems, you can't recover the cycle bit strings from the jump bit strings. But I think you should still be able to at least estimate whether refrigeration or engine cycles are more likely, because just looking at the statistics of how the jumps are happening, right?
Yeah. So it's not only about 3 level systems. I mean, you can do it with n level systems, but it's more this assumption of single excitations. So you can have a system like Sarah was saying, you know, you can have multiple dots. That would be a state with many, many levels. But if you assume that there's at any given time just one electron in the system, then you can identify cycles. If you go beyond this kind of single excitation assumption, then it does break down. You're right that you can estimate essentially the probabilities of kind of things happening in one way or things happening in another way. But that's kind of like a steady state thing, right? You cannot identify, like, if you just look at strings and so on, you cannot really identify individual cycle events. But you can, of course, you can characterize the steady state properties of the machine. You cannot you just can't look at it from a single shot and uniquely identify what is the cycle. That's kind of it.
Okay.
Hi, thank you for the talk. In the results you showed in the very last part of the talk, no, sorry, not that very last. I mean, the same top, yes. So the microscopic model behind all of that is what you have just shown a couple of slides before, right? It's a master equation. You have a work reservoir and two baths, right?
Yeah.
In that results, do you actually have any work reservoir?
No, in those examples, no. We have a unitary work, but no dissipative work. So I mean, kind of our formalism does allow you to have work reservoirs. That's fine. But in that example, there are no work reservoirs.
And the second question, the unitary part, like the Hamiltonian part, is it It's a very basic question, actually. Is it constant or is it time dependent? I mean, is it a driven system actually, or the every dynamics comes from the coupling with the two best?
That's a good question. So it is time dependent. Sorry, I don't know if I included it here, but anyway, it is time dependent. This drive will have a driving frequency, but then you do the trick of going to a rotating frame where you can eliminate the time dependence. So like in practice, we don't have to deal with a time dependent Hamiltonian, but physically speaking, it is a time dependent Hamiltonian. And just one kind of quick comment. So we are assuming here, just because it's interesting that this kind of drive is unitary, right? But you can also replace this with a work reservoir. It's essentially the incoherent version of the tree-level model, right? Which is in some optical experiments, people actually use this. Essentially replace this with like incoherent jumps, whereas here we're using kind of Rabi oscillation kind of thing.
Thank you.
Hey, Gabriel. I have a question here. It's like, have you considered the reanalyzing this from inserting a Maxwell daemon in your machine? I mean, considering that you know that which jumps are let's say, favorable and the ones that are not?
Yeah, no, so we are looking into this. There's one student that is actually exactly working on this. The basic idea is that in the most general case, sorry, if I can just go back a lot, okay, fine. In the general case, your data string is this kind of full string of x, 1, and n. The most general kind of feedback that you could do is some kind of recipe that uses the entire data string and comes up with a decision about what you do. It's like, you observe an entire string of data and you say, okay, based on this entire string, I'm going to apply some operation, right? And that, of course, you can do it, but it's very complicated. What we're looking at now is, okay, suppose I use, a few of the data points, maybe just the last one. That's the simplest case. People call that current resolved feedback. But maybe you can use kind of slightly more complicated combinations of your past data. And then for this kind of a tree-level model, it does become kind of interesting because suppose you observe essentially two jumps, right? Then with two jumps, you can pretty much know exactly what you need to do about the system, even for a multi-level system with more than 3 levels. As long as there's a single excitation, it's kind of nice that you don't need the full data history. You just need like the last few. But we are starting to play with that a little bit. Yeah.
Anyway, yes, I was thinking, have you tried to characterize quantum phase transitions with this? I mean, you can always have a chain and with different regimes and with these stochastic processes. You could think of doing that.
So what we've looked at is for the optical Kerr model, which is essentially, it has a first order and second order phase transition. What is the statistics of quantum jumps? So not exactly this, but essentially looking at this kind of higher order statistics for those things. And Adalberto, who is here in the audience, he's looking now at essentially the similar model that Gabriele presented, this kind of time crystal, and essentially trying to analyze, again, statistics of unravelings and so on for these models. That's kind of the extent of what we looked at. This exact idea, not so much. Yeah.
Because here you could see, for example, the first that come to mind is a transition between an insulator and a metal.
Right,
because you have a transport.
Right.
So you could see it on the stochastic jumps. Would be interesting to see how the transition would be characterized in that sense.
That is interesting. Yeah, I'll think about that. Maybe we can discuss.
We can discuss it later. That would be very nice. Yeah.
Yeah, thank you for your talks. And I wonder because the kind of first excitation ansatz is very good to make the jump bit cycle bit string of cycle, but we can get some of the bits string of the jump which cannot be explained by the first excited by the simulation or experimental. So how can you handle that kind of bit string of jump? So we cannot do anything. Or...
So sorry, is the question that not all bit strings of jump can be converted into bit strings of cycle?
Yeah, because you have some assumption about the first excited. So sometimes we get some bit string of the jump which cannot be explained by the forced excitation and assumption. So how can you handle that kind of bit string?
Yeah, no, I mean, I'm not sure I'm going to have a good answer to that, but essentially, you know, in general, yeah, I mean, if you observe bit strings, there's only so much you can say about what's going on to the system, right? I think this is actually a very good example. Like here, you know, you observe a very silly kind of bit string, very small, but there's a lot of possible configurations that the system can be in. So you learn something. It doesn't mean you learn a lot, and that is a kind of a challenge overall. So that's why we're kind of approaching this, trying to, you know, kind of divide problems into classes where we can learn a lot, classes where we can learn less, and so on.
Okay, so you partially answered maybe. So your formalism is so general that you can have, for instance, coherent buffs or squeeze buffs.
Yeah.
And you partially answered, so in this three-level system, you talked about work reservoirs, and so maybe coherent buffs or squeeze buffs could be thought as work reservoirs, no? But can you see some effects of the coherence in the bus from the symbols emitted or from some measurements that you can do on the reservoir, on the ancillas, so that you see that some advantages or some modifications due to the coherence in the bus?
I mean, we haven't looked into that, but I do suspect we can. Just kind of a quick comment is that, of course, when you do introduce, say, more exotic non-equilibrium BEVs, there's a relevant experimental question of, you know, can you actually observe jumps of these BEVs? And I mean, that's kind of problem dependent. But for these kind of work reservoirs, you don't need to observe their jumps. You assume that they're like physical reservoirs, like, you know, standard heat BEVs, that you do observe those jumps. So there's only some of the jumps that you observe. And then there could be non-equilibrium work reservoirs. And then in that case, yeah, I mean, the whole formalism apply equally. Yeah, I mean, that's the extent of what we looked at. Maybe one other thing is like, we looked at essentially fermionic spin chains where you have pairing terms like C1 dagger, C2 dagger kind of thing. And that's kind of like, you know, spontaneous production or annihilation of particles within the chain. And essentially it messes everything up, but yeah, you can still say something, but a lot less. Yeah, that's kind of
thanks.
We're going to have just one more question and move to the next speaker. Just a second.
Gabriel, thanks for the nice talk. So at the very last level of simplification of your description, you have this data sequence of this time series, right?
Yeah.
Which is basically a classical random walk at the end, forward, back. Is there anything in the statistics of this random walk that has a quantum signature as of itself?
So are you talking about like the general kind of bit string or?
Yeah, like backward, forward, backward, jump, back, forward.
Right. So for this model, it's very, the statistics are kind of simple because the cycles are actually independent of each other for the three-level model or the double dots, right? Every time a cycle completes, the next cycle is completely independent of the previous one. If you have more complicated models within the same kind of paradigm, you can have cycle correlations. And then it is kind of a random walk, but it's more complicated because your data can have really kind of long and complicated correlations. Yeah, exactly. You're absolutely right. That was part of the motivation for us because, you know, if these excursions, like, you know, you can enter this region B from here and then leave from here and so on. So each excursion is not independent of the previous one, right? If this had only one state on it, they would essentially be independent, what we call renewal processes. Yeah, in general, they aren't. And so there's kind of interesting and usually complicated correlations.
Yeah. And do you expect there will be some quantum signature in these correlations? That's the question, really.
That is a good question. I don't know. So for excursions so far, we've been playing mostly in classical systems. We actually found there's a lot of like cool stuff that you can do. So again, Guilherme can you know, poster has all of the information, but we so far have been playing mostly classically about it because this idea of excursions, you kind of need to monitor the system. So you need to know where the system is jumping on. And this requires, you know, that either the system is actually classical or that you're monitoring, you know, the populations of the system, which means that there will usually be strong decoherence, right? So we haven't really looked into, you know, what happens when you have quantum effects. Maybe one last comment is that a nice thing about this kind of excursion business is that you can think about region B as being kind of a dark region. And that could be very quantum-y. It's like, A is like the visible region that you can see. It's kind of classical. But then when the system goes into B for the first time, you don't really see, and there's quantum like wobble happening. And then eventually you see the system back again. And then you can ask the question, what happened during this excursion to this kind of quantum regime kind of thing. And that's one of the things that we're starting to think. Yeah.
Okay, let's thank Gabriel again.
Yes.
Tem que descobrir para onde que ele está apontando, né?
Eu demorei.
Tá, tentar 4 vezes. Acabou em 4, mas tem 5 perguntas. Well, the next speaker is Carmen, and she's a researcher to be here at CBPF. The floor is yours, Carmen.
Thank you. Can you hear me all right? Is the mic okay? Yeah. Thank you very much. Thank you to the organizers for putting up with me and letting me speak here today, because we're going to keep on the topic of excursions, and we're going to go on to something that is a little bit out of the field and different from what you've heard the past few days. I'm really not from the quantum thermodynamics community, so I've been learning a lot. And I please ask you to bear with me through my ignorance in this talk. But the work I'll be presenting today is work that I've been doing in Cambridge for the past 2 years with a number of very talented students and in a very close collaboration with Mette and Hannah. Since I'm not from the community, I thought I might introduce myself a little bit. So like I said, I've been in Cambridge for 2 years, but before that I was in Groningen in the Netherlands. It's a little city up north. It's very beautiful. I do recommend a visit, even though it doesn't look like this most of the days. It looks like this. After wrapping up in Groningen, I moved to Cambridge, which is also a very beautiful city, even though it doesn't look like this most of the days. It looks like this. So when I went from Groningen to Cambridge, I told my partner, I'm not going somewhere that has less sun days in the year. And it turns out that Cambridge has about 2 extra days of sun per year than Groningen. So that's where we ended up. And I think I've kind of overshot it this time, especially seeing the weather this week, right? So now we're moving to Rio, and I'll be joining the team here in this very institution soon. So if you're interested to have a chat and talk about possible ways we can work together, I'm very happy to hear. Throughout my work in these 2 places, I've been working with artificial atoms in the solid state, and I'll tell you a little bit about what I mean with this. But I've been specifically looking at systems where different degrees of freedom play a role in determining their properties, right? And I thought, well, maybe it's a good place to come, a conference like this, to learn. Like Marcelo said a few days ago, we can learn a lot about a system by talking about it in different terms. And I've been kind of hoping that you would teach me how to look at these systems in a different way, right? So in a way, this is a very, very selfish talk, and I ask for your forgiveness in that, right? I'm trying to learn. What I'll do is I'll present to you one specific system that I've been looking at that I think is very interesting, in the hopes that we can come up with new ways to describe it together, right? So these systems that I've been studying, they're very useful in terms of quantum technologies, very generally, because they can work as optically accessible quantum memories, right? So these are spin photon interfaces where you can imprint an optical degree of freedom onto a spin degree of freedom in the solid state, right? Particularly in the community, in the solid state community, there's 2 platforms that have been kind of at the forefront of the developments. And these are contrasting platforms in a lot of ways. So on the one hand, you have Diamond and color centers in Diamond. So these are systems that are really atomic defects, and Sergio will tell a little bit more about them tomorrow, but they're atomic defects in the diamond lattice, right? So they work as trapped atoms in this material. And in that way, you can access the electronic degree of freedom, but you can also access individual nuclear memories in the environment, for instance. The NV particularly, which is one particular color center, operates at room temperature for some types of applications, right? And the other end of the spectrum, you have semiconductor quantum dots, and typically they're fabricated in these 3-5 semiconductors. So these quantum dots have an electronic state that is very, very large compared to these atomic centers, right? So they're tens, maybe hundreds of nanometers large. The 3-5 materials are nuclear spin abundant materials, so they have a bath of nuclear spins that is always present. You can't purify it away. So these means these quantum dots are always, the electronic spin that is trapped in it is always interacting with tens of thousands, maybe millions of nuclear spins, right? And these nuclear spins function as a bath that causes decoherence, right? So from the point, and then in the middle, there's the system that I'll tell you a little bit about today, which is hexagonal boron nitride. It's a layered material. It's also a 3-5 material. So boron and nitrogen also come from the 3 and 5th families of the periodic table. But it also has this very large band gap that that enables the appearance of these atomic defects in the lattice. And I'll tell you a little bit about how this system falls in between these two different material platforms. So from the point of view of many body physics, diamond and quantum dots are very different for a lot of the reasons that I've just outlined to you, right? So like I said, in diamond, the electron spin is interacting with individual carbon-13 atoms that may be present in the lattice. This interaction is on the order of a megahertz or below that. So you can address individual nuclear spins that are in the material. Whereas in the quantum dots, you have this interaction with this very large bath, right? And so here is an example. This work is not done by me, but by very talented people in the group that I was working on, where you can see these Rabi oscillations of the electronic spin. This is an optical Rabi experiment, but you can also see these sidebands, and these sidebands are an imprint of the hyperfine coupling to the bath of nuclear spins, right? And this hyperfine is then of the order of about 100 megahertz. So like I said, I've been working with hexagonal boron nitride. It's a material that it's a little bit in between these two. It hosts a series of different defects that can be optically active as well, but it's also very much compatible with nanofabrication. So compared to diamond, for instance, which is a very hard material and hard to fabricate on, technologically, it's a very interesting material because you have access to these nanofabrication tools. If you look at the optical spectrum, HBN has defects that span the entire optical spectrum. So here in the blue, you have some emitters that are single carbon vacancy, so these carbon impurity. So these are single carbon atoms that are put into the hexagonal boron nitride lattice. These things are very good single photon emitters, but they don't have a spin, right? So you don't have a spin photon interface. Now, in the red end of the spectrum, you have these boron vacancies. So this is a single boron atom that is missing. This system forms a spin 1 defect. So it is a defect that has a spin 1, but it has very weak optical transitions, so weak that you can never look at a single system on its own, right? The optical signal is very small. So you always need to be looking at ensembles if you're working with these boron vacancies. They have been used quite extensively already, even though they've only been discovered a few years ago for sensing applications, for instance, because it's very easy to put hexagonal boron nitride on top of something that you would want to sense. But these things also don't work as an optimal spin photon interface because of this. You have a spin signal, but you don't have a single emitter, right? And we've been looking at some defects that operate here in the yellow to orange end of the spectrum. So they have optical transitions around 600 nanometers of the spectrum. You can see these defects at the single defect level. So this is a confocal image of one of our samples where we're collecting PL and scanning the position of the excitation beam on the sample. And you can see these individual blobs over here. And each of these is a single defect that we're addressing. Right. And we've been interested in sort of figuring out what are the spin characteristics of this and how does the material, this intermediary material actually impact the properties of these things. So the material that we look at, it's hexagonal boron nitride, and it's grown through metal organic vapor phase epitaxy. So these are all names that you don't really need to know, but all you need to know is that these things can be grown at the wafer scale. So this is a sapphire wafer that is covered with ore material. And we can then sort of delaminate the HBN from the sapphire wafer and transfer it onto any substrate that I would want to operate with. And the other thing you need to know is that this growth process helps incorporate carbon into the lattice. So the specifics, the chemistry of this growth process favors the incorporation of carbon into the lattice. So all of these defects that we are looking at, we have reason to believe that they are carbon related, right? And I'll tell you a little bit more about this. And the experiment we're performing is an experiment called optically detected magnetic resonance, right? So if you've heard of NMR or EPR, these is a very, very similar technique, but now we detect everything optically. So in our setup, we have this microscope objective here. That's the one. It sends light through our material. It collects the PL that is emitted back. And then we have a coil that is actually very artisanal that you can see here. And we can use this coil to apply microwaves onto our sample, right? And finally, we can bring in permanent magnets close to our material so we can also apply weak magnetic fields. What we do is we shine light onto our sample. And this light works both to initialize the spin of the system, and I'll tell you how that happens just in a little bit, but also works to enable us to read out the spin of the system. And then we shine microwaves and we collect signal and references. And when we do this onto this particular defect at zero magnetic fields, so we scan the microwave frequency, right? And we collect the light that is emitted by these defects as a function of the microwave frequency. And at zero magnetic field, we see 3 individual resonances for these defects, right? With contrast that goes up to 50%. So this is, it's a relatively large value of contrast. For some applications, it can be very useful. If you're doing sensing, for instance, you want to have very quick readout. So this contrast can be very interesting. And the presence of these 3 resonances allows us actually to start to determine the electronic structure of the system. How does it actually look like? And the fact that we have 3 resonances at zero magnetic field immediately tells us that we have a spin 1. So this is a system that has a spin 1 in the ground state. Now, I told you that I would mention how you get this readout for this ODMR experiment. What happens in these systems, and it's similar to what happens in the NV centurion diamond, is that you have a system with a ground state that is a spin 1, an excited state that is a spin 1. You can drive optical transitions between these things, but you also have a radiative, a non-radiative decay path here through a singlet metastable state, right? And this non-radiative decay path is spin dependent. So the probability of going into the singlet manifold and coming back from it depends on spin. And that immediately gives you an optical fingerprint of the spin of the system, right? You're more likely or less likely to emit photons depending on what spin you started with, right? So this is what's happening here. You always have spin initialization. And then once you hit resonance with one of the 3 possible transitions for the spin 1, you get this signature over here. Yeah. The presence of 3 independent resonances at zero field also tells us that this is a low symmetry system. So if this were a high symmetry system, this E parameter here would be quenched and you would only see 1 resonance at zero magnetic field, right? We can confirm this low symmetry by actually applying a magnetic field and rotating the orientation of the magnetic field and collecting these resonances and then modeling them with this spin 1 Hamiltonian. I won't go into a lot of detail on this, but all I want to tell you is that this confirms that the symmetry axis of the system is in plane, right? That this is a low symmetry structure. So far so good. We have a system that has a spin 1. You can observe it at room temperature optically. Can we actually drive coherences out of this thing? And then the first time we tried it, so we go onto this resonance, we park our microwave frequency over here, and then we tune the length of the microwave pulse, and we can see these nice Rabi oscillations that persist up to a microsecond, right? So this, again, it's a system at room temperature in a material that is a nuclear spin full bath, right? So we really didn't expect this, to see this microsecond long Rabi coherence time. Well, it turns out this Rabi coherence time is not actually a useful coherence time scale, right? It's the time at which you can drive the system, but it doesn't tell you anything about how long can you use these coherences for. So in order to characterize that, we go to other experiments that, especially if you're familiar with the NMR community or the EPR community, you would be familiar with these. So first, we drive Ramsey oscillations of the system. So here we apply a pi/2 pulse. We place the spin into the equator of a Bloch sphere. So we create spin coherences. We let it evolve for a certain time. And then with the second pi/2 pulse, we map the system back onto the optical readout basis, right? And when we do that, we see that these coherences actually now die out within 100 nanoseconds. So we went from 1 microsecond for the Rabi drive time to 100 nanoseconds only. I mean, not too great, right? We can then try to start to correct for magnetic noise in the environment by applying pi pulses in something that we call the Hahn-Echo experiment, right? So here, I apply my pi/2 pulse, I create my spin coherence, and then halfway through my precession, through my coherent evolution, I apply a pi pulse. And this pi pulse actually flips my populations, and it allows me to correct for static magnetic noise that has been experienced within this evolution time. And then I extend my coherence time, so I gain a factor of 2, but still an order of magnitude away from what I started with, right, in my Rabi experiment. So what we can do is we can keep applying these pi pulses, right? So we can add pi pulses, and each pi pulse that we add, we are actually flip-flopping my population in the Bloch sphere, and I'm correcting for noise that is evolving faster in the material, right? So these pi pulses act as a filter function for magnetic noise that is present in the material. And as I do that, and I monitor the contrast versus the free precession time, I see that I start to extend my coherence time further and further, right? So we've, at that time, we had added about 10 pi pulses to our evolution, and that had brought us to about a microsecond. So we've now recovered the microsecond that we started with, right? What's interesting here, or one of the things that are interesting here, is that, like I just said, these pi pulses, they are acting as a filter function on the magnetic noise in the environment, right? So actually, the dependence of this spin coherence time on the number of pi pulses that I apply tells me something about what type of magnetic noise I'm experiencing, right? And that information is actually encoded in the power in the power law dependence between this spin coherence time that we extract from these measurements and the number of pi pulses. And if we would have something like the NV center in diamond, where the noise bath is uncorrelated, each carbon that is in the environment doesn't really know that the other carbon exists. These things are evolving very independently. I would have a weak dependence, or a 0.7 dependence if you're looking for the specific number. A weak dependence between this coherence time and the number of pi pulses. But if I'm working with quantum dots, for instance, where the magnetic noise is correlated, right? All of these nuclei, they know of each other's existence through the electron spin, right? The electron spin is actually connecting all of the nuclei and the gallium arsenide back together. Now, if you would have this case, you would have a very sharp dependence or a sharper dependence between the spin coherence time and the number of pi pulses. And when we look at what we observe for the system, we see a dependence that is about 0.78, which is slightly higher than what you would have for diamond, but definitely a lot lower than what you would have for quantum dots. So even though we're working in this nuclear spin rich environment, we're actually not experiencing a correlated nuclear spin bath, or to a much lesser extent, right? Very recently, we've had a very talented student, Dylan, who has been working very hard on extending these pulses further. And he's been able to push this coherence time to about 20 microseconds. And we know at this point that this is limited by the microwave pulses that we can apply, right? So if we would have a more intelligent microwave setup, we could push this further probably. Now, this is all the experiments that I've shown you to this point have been performed at zero magnetic field, which is, if you're working with these systems, you could have told me, well, why don't you apply magnetic field and you'll decouple the nuclear spin baths and possibly extend your coherences. Well, it turns out that as soon as we start to apply a magnetic field, we start to kill Rabi oscillations, or the system experiences noise that is evolving faster. And we can actually trace that back to the electronic structure of this system, because we have actually at zero magnetic field, we have an anti-crossing point here. And at this anti-crossing point, what happens is that my energies don't depend, or they have a very weak dependence on magnetic noise. So this actually helps protect the electronic spin from this noise bath, right? So we're actually at lower magnetic field where we're starting to turn off hyperfine coupling to the electronic bath because of this anti-crossing here. Yeah. We can also see that from the line shape of our resonances. So we start off with relatively narrow line shape that is very structured. And as we apply a weak magnetic field, that line shape broadens and it becomes a lot more featurey. And that is related to the onset of this hyperfine coupling as you move away from this anti-crossing point here. Right, so in this system, we can turn on hyperfine coupling by moving away from the zero field operation. The last thing I want to tell you is that we can actually model the shape of this ODMR resonances, right? And without going into the details, what we extract when we perform this model is that the dominant hyperfine coupling that we observe is to only a pair of nuclei, and this hyperfine coupling happens with a magnitude of about 20 megahertz. So if we go back to what I showed you in the beginning about the sort of dominant platforms in the community, we see that hexagonal boron nitride, or at least these defects in hexagonal boron nitride, really operate here in the middle between these two. So it's a regime that we haven't really explored yet, because we know how electron spins coupled very weakly to individual nuclear spins behave. And we can actually trace back the behavior of the bath in quantum dots, and we can, to a very large extent, understand how hyperfine coupling influences the spin coherences and so on of electron spins in quantum dots. But this intermediary regime, that's not something that we have explored a lot, I think. And that's where I would like to learn from all of you and gain a new language in order to track this problem, actually. Now, why does this hyperfine coupling appear this way? We think we understand this. Like I said, we think that these defects are related to carbon impurities in the lattice, and that they are the electronic state is largely localized in pz orbitals of the carbons. So the electronic state is actually largely localized on top and the bottom of the boron and nitrogen layers. And the contact interaction term between the electron spin state and individual boron nuclei is small. Right? We think that this is the origin of this. But beyond this, then this actually opens up a very interesting path, because we don't know the microscopic structure of these defects, but we know that different carbon moieties can live in HBN. right? So for the field that does organic molecule NMR, for instance, this can be an interesting perspective as well, because we can create molecules that would not be stable otherwise in HBN, right? If we have the control over where these individual carbons can live. So this can be an interesting perspective as well. So finally, I hope I haven't bored you to death with my detour, but we are excited about these systems. It's an interesting material platform from the technological point of view, but I think it also brings in new physics and physics that we haven't really explored so far. These particular systems, they are bright and optically addressable. They operate at room temperature, which makes the experiments a lot easier, for sure. And the material platform is also very interesting. I'll just skip this and leave you with one of the last pictures that we took in Cambridge. Thank you very much.
Thank you, Carmen, for the nice talk. Any questions?
Hi, thank you for the very nice talk. Can you maybe go back to one of the first few spectra that you showed, the one that had like a circle with a photo of someone? Yeah, that one. Okay, maybe you already explained this, but I maybe didn't get it. Could you just explain what are the three peaks physically meaning, essentially? Yeah, this is very common for defects in solid state material, but or molecular systems actually. But this is a PL spectrum, right? So this is light emitted by the defect, spectrally resolved. This is what we call the zero phonon line. So this is direct transition between excited and ground state. And the next two are what we call phonon replicas. So these are optical transitions that involve a phonon as well, the emission of a phonon. Yeah.
So may you explain why correlations in the bath will give a different power law, different exponents on n pi? Because I guess, as you said, it's just the filtering. So, I mean, you may have the same filtering, and how can you distinguish between correlated and non-correlated?
Well, yes and no, right? Because the dynamics of the bath is different. So it depends on the dynamics of the bath, the time scale at which the bath evolves in a way that you cannot correct for anymore, right? And a correlated bath evolves faster, but you can correct for it.
Right. So, okay. So let me say, so probably it's a theorist. So I can invent an uncorrelated bath with some spectral function, which will give me the same dependence, no? Because if I change the spectral function, I guess, so this is my
you could be right that it's more related to the spectral function than to the correlations. But I would say that experimentally we observe these together, right?
Any more questions? No?
Thank you, Carmen, for a great talk. It's a very interesting system. So I'm puzzled by some of the features that you mentioned. One of them is actually the one that at zero field and increasing the field, you have a shorter Rabi oscillation period. Yeah. So I was wondering if you thought about that, or if it's this feature here, this protection mechanism that you were describing. I'm not sure if I completely understood, but it sounds a little bit like these Landau-Zinner effects for the anti-crossing process. Is something like that?
Yeah, it's very much related. It's an anti-crossing. It's a partial. Some people call it a partial clock transition. It's a very particular clock transition because it's only one magnitude that you're protecting against, right? So it's not a great clock transition, but it's a partial clock transition. Yeah.
Okay, interesting. Thank you.
I mean, thanks. Concerning that first oscillations that you say is 0 millitesla, did you compensate for the Earth field?
No.
So it's not actually 0 millitesla.
Yeah, it's 60 microtesla.
It's possible to compensate for that.
Yeah. And it would possibly get better. Yeah.
Okay.
Thanks, Carmen, for the talk. Have you analyzed also like two of them talking to each other, things like that?
Yeah. So eventually we would like to move to sort of photon interference from two different emitters, but we don't have the optical coherence yet to go there, right? So we're looking at the optical coherence. To look at two individual defects talking to each other, it's hard because it's hard to disentangle what signal comes from one and what signal comes from the other. And they occur sort of statistically in our samples, right? So sometimes we know that we have two emitters because we do a G2 and it's a 4 anti-bunching. And we know that we are collecting light from more than one. And then whether the spin signal that we're seeing comes from both or comes from only one, then that's hard to disentangle, right? Yeah.
And have you also analyzed building these structures inside nanowires and things like that?
Yeah. We're working on it. Yeah.
Any more questions? No? Let's thank the speaker again. We have a break now on the morning part of the conference, and then in half an
How much time do you have? I have 35 minutes.
Yeah.
Okay.
40 to 12.
Oh. It's hot. We'll keep it short.
Oh, can leave before, yeah.
Oh, the lunch. I like that. But it's also hot, so.
So welcome back. Let's start the second session of the morning. And then now we will have Sebastian Defner from UMBC. Sebastian, the floor is yours.
All right, great, thank you. So first of all, thank you very much for bringing me back to Brazil. It had been a couple of years and I really enjoy being back and interacting with all my friends. When preparing this talk, I was trying to find something that was topical and interesting to a broad range of you. And then I realized that a couple of things that I've been doing over the last 5-6 years or so originated in a conversation with Sergio. About 7 years ago, I visited Campinas for a couple of weeks, and for an extended day trip, essentially, I went to Sao Carlos. And Sergio told me about all this great work that he had done with PECs, and we started talking about how to extend quantum thermodynamic notions to both Einstein condensates or more broadly to nonlinear systems. And what I will be presenting today is what I've done most recently in the context of thermometry, or the question is, how do we build better thermometers using nonlinear effects such as in BEC? But what I really will be doing is, over the next 39 minutes or so, I'm going to talk about 2 papers that I recently wrote. And the first one was, so whenever I don't really understand dynamics, the first thing I do is I look at speed limits. Because speed limits are a safe place for me, so I know what to do, I know how to derive things. And then I try to understand the dynamics, and in particular the thermodynamic properties of a system, through the lens of what I can say about quantum state evolution. And what I will be talking about here specifically is I will be deriving, not really deriving, more computing, going to show you a couple of pretty pictures for the nonlinear Schrödinger equation, in particular the Gross-Piryevsky equation. And I will make a very strong argument that some of these systems are interesting, not just from a scientific point of view, but also pedagogically, because there are many analytically solvable examples. Personally, I was very excited when I was able to solve a Gross-Piryevsky equation analytically. And you're going to see that here. But fair warning, I'm not going to show you the math because it's just ugly special functions. I'm going to show you the pretty pictures. And then in the second part, I'm going to talk about this most recent archive paper where I generalized some of these ideas that I developed in this paper here, and then started asking the question, so once I understand the speed limit and I find these quantum speed ups that you will see, how do I use them for something interesting and useful? And in particular, is there any thermodynamic consequence that I can exploit? And then maybe start thinking about further development of nonlinear quantum devices. And in particular, what I will emphasize again is there's a whole zoo of analytical solutions to problems that are tractable, but I also will mostly focus on thermoqubits because this makes it easy and it becomes very simple to understand how nonlinear dynamics are different from linear dynamics. And I will make clear what that means. All right, now I feel like after Diego's talk, I don't really have to say anything about speed limits anymore because he gave this beautiful survey of the zoo of speed limits that is out there. But I do want to highlight a couple of things that will be important moving forward. So here I just mentioned this PRL from 2009, but speed limits go back almost 100 years. And in this paper, they made it clear that the unified bound, which is the Mandelstam-Tam bound and the Margaret-Levin time bound, are tight, which means they're attainable at what I do want to draw your attention to is, so we've spoken about the uncertainty in the Hamiltonian. So that's essentially the variance or the energy above the ground state energy, which means the amount of resources that are available. But what I want you to notice is that both of these speed limits are proportional to pi half. And where this pi half originates is that in both of these papers, the question that they're asking is the following. Assume you have an initial state that is well described that you know. What is the minimal time a quantum system will need to evolve to an orthogonal state? Naturally, these speed limits then should be proportional to the distance that the quantum state traversed in Hilbert space. And that's exactly the angle pi half. That the situation is not that simple becomes obvious when you generalize these quantum speed limits to arbitrary angles. So I'm using here this curly L. Curly L is the Bourse angle for the experts, but just think of that as the generalized angle in Hilbert space between quantum states. And for the variance bond, the original bond, you see that you get exactly the mapping that you would expect. The pi half is just replaced by the angle. But then here for the newer one, for the Margulis-Levitin bond, things become significantly more complicated. And what I'm writing here is it's not exactly what they have in the paper. In the paper, they show numerically that this should be true, but they also write explicitly that they failed to find a rigorous proof. And the exact shape of this bond is also not that important. What is important is that, in principle, quantum speed limits are complicated and it depends very much on how you measure distinguishability. Now, for quantum states, pure quantum states, you just think about angles, which is a natural distance. But then, as Diego was already saying, there's a huge zoo of different things that you can measure. And basically, whenever you think about quantum state evolution, you need to first decide what you want to call a good measure of distinguishability. And that depends very much on what you're interested in. And then this now, I used to say recent review, but now it's actually a pretty old review. We put together everything that we knew 2017. And as Diego was saying, there are a lot of generalizations to open systems, driven systems, and you name it. One thing that is particularly interesting about these speed limits is that originally they were derived for unitary dynamics. And very generally, we found that whenever there are additional quantum features, such as quantum coherence, quantum entanglement, anything that is not classically available, usually we can exploit this as a resource to speed up quantum evolution. The reason why this is important is when I want to think about nonlinear systems, then the question that I asked was, well, nonlinear systems seem to have this additional term in the evolution equation, and I will make this precise. But the question is, this modification to the linear dynamics, can I exploit that to do better? Can I exploit that to enhance quantum state evolution? But in order to do that, I need to generalize first these speed limits to something that is amendable to nonlinear dynamics. And one thing that we don't necessarily appreciate when looking at this is that this very much depends on a notion of linear quantum mechanics. So when we think about quantum mechanics, the first thing that we do is we usually compute eigenstates and eigenvalues and all of that. And these speed limits are literally derived from looking at the dynamics or the properties of eigenstate evolution. If we go to other quantum dynamics that are nonlinear, then this language of eigenstates and eigenvalues doesn't carry over anymore, which means we actually need to start thinking more carefully about what do we mean by quantum state evolution. Luckily, this is something that also had shown up in the literature already. So in this paper, I was thinking mostly about information propagation. I was thinking about how do I derive speed limits for things like the Shannon information of von Neumann entropy and all of that. And what I realized was that most of these speed limits really can be traced back to the rate with which a quantum state evolves. And you can show quite generally that the quantum speed limit, so the rate with which the state evolves, is always upper bounded by, so here I write the Helmholtz-Schmidt norm, the square norm, the Euclidean norm of the quantum state, but more generally, really the norm with which the quantum state evolves. I think there was a question the other day about time and how for a driven system, time is related to quantum speed limit times. So you play these funny tricks. So you reintegrate and you reintroduce classical time parameter. So often you find in the literature something like this, quantum speed limit time, where, however, this time is a classical external control parameter, which doesn't really have any particular meaning. So in what I will be doing moving forward is I will be focusing on the quantum speed limit, so the rate of quantum state evolution, which is just clean and free of all of these interpretational issues. One thing that is interesting is that if you just plug this in, so depending on the norm that you're using, right, so you get the commutator from the unitary evolution. So you essentially get the variance of the energy back, or depending on if you use the trace norm, which means if you have a 1 up here, then you get essentially the average energy back. Now, the question that I want to ask is, using this notion of quantum speed limits, rather maximal rates of quantum state evolution, what can I say about nonlinear dynamics that are fundamentally different? To fundamentally, and let me make this very precise. The bounds that we've studied are for linear quantum dynamics. If I change the dynamics in a nonlinear way, can I use this additional nonlinearity as a resource? Can I do something useful with it? And if so, how? How do I quantify that? Well, first, then I need to think through where do these nonlinear dynamics even come from and what do they mean? And if you look into the literature, there's a huge zoo of different nonlinearities out there. most famously probably in nonlinear optics. As I was saying, I started thinking about that, motivated by Sergio, who convinced me that the thermodynamics of BCs is important. So a quick, very quick overview of what to think about. So if you have two bosons, then introductory statistical mechanics, two bosons are described by an even superposition of wave functions, which means that multiple bosons can occupy the same quantum state, and for fermions you would get the minus sign, where the minus sign is just the Pauli exclusion principle. Now, what we also know is that for very high densities or rather low temperatures, you get this famous Bose-Einstein condensation, which means that all of these bosons condense into the zero momentum state. Okay, that's something that we need to appreciate a little bit. That's a little bit weird when we think about quantum state evolution. But what we're talking about here is the evolution of the quantum state, not the particles themselves. In BECs, we just lose this notion of single particles. What we then have to think about is a macroscopic quantum state that carries some interesting correlations. The problem is, if we want to do that analytically, and in particular, if we want to solve the exact dynamics, we have to solve a complex quantum many-body problem. And whereas for fermions, we still know how to do that, right? You have something like Slater determinants that allow you to efficiently compute the quantum state. The quantum state for bosons is NP-hard. Strictly speaking, you need boson sampling in order to solve for bosonic problems. So there's no hope that we can do anything analytically or numerically. However, thermodynamics comes to the rescue. And using essentially Ginzburg-Landau theory in mean field, you can express the bosonic Hamiltonian as a 5-4 theory. And then in mean field, what drops out is the Gross-Pitaevsky equation. The one thing that I should emphasize is this is phenomenological modeling. And depending on the type of interaction that you include in your model, you get different types of nonlinearity. What we're most familiar with are Gross-Pitaevsky type nonlinearities. But there are many other things that we can do. But I want to focus on Gross-Pitaevsky first and then talk about the others. It's quite interesting. So I didn't really put any references here because nonlinear dynamics just pop up everywhere. If you just Google nonlinear dynamics, you will find, sure, Gross-Pitaevsky and bosonic systems, but then you're going to find this entire zoo of nonlinear optics problems, and there are now thousands of textbooks on nonlinear optics and things that you can do. But then they also pop up in plasma physics and interacting spin systems, and you name it. So they're pretty much everywhere. But the way that I think about them is they are always effective descriptions of much more complicated problems that we wouldn't be able to solve otherwise. All right, so the Gross-Pitaevsky equation is the most famous nonlinear Schrödinger equation, looks very much like this here. And then when I say very much like this, there are a couple of subtleties that we should be aware of. So I'm writing this as a time-dependent Schrödinger equation. The physical interpretation is, well, this psi, it's not really the quantum wave function, it's the order parameter. But we can pretend that this is the macroscopic wave function if we normalize that properly. If we normalize it to chemical potential, then it's the order parameter. If we normalize it to 1, then it's just the usual probability density. We can have time-dependent potentials, like we always do in thermodynamics. I'm going to see an example on the next slide, like driven harmonic oscillators or something like that. And then the interesting part is that you get this additional nonlinear term here, which is an effective description of the cooperative interactions of the bosons. So you notice that I hesitated. So we're still talking non-interacting particles. But because of this bosonic freedom, we can pretend as if there was an interaction. That's something that we're much more familiar with in fermionic systems. So we usually include this additional Fermi repulsion. But we can do something similar for bosons where you get an effective attraction. Now, if you go through the analysis, so I'm just writing kappa as the strength of the nonlinearity. But this can be made very precise. So this is just related to the scattering length, which in principle is also experimentally controllable. Now you immediately see why speed limits for such equations are interesting, because as I've just shown you on 2 slides previously, let's just go back. So here, speed limits are just given by the rate of quantum state evolution. And now if you look at this evolution equation, everything that has changed is that I have an additional term on the right-hand side. If there's an additional term, if it's positive, so you have the usual bosonic attraction, then we know that the norm of the right-hand side has to be larger. So it's almost obvious that quantum state evolution in BECs, or for the Gross-Pitaevsky equation, has to be larger. But it's not quite as obvious as you would expect, because this thing still depends on x, and this is actually a nonlinear equation. And as I was saying earlier, we're very much used to thinking about quantum mechanics in terms of linear evolution equations, eigenstates, eigenvalues. This thing doesn't have any eigensolutions anymore. It has stationary solutions, but the space is not spanned by eigenstates because it's a nonlinear problem. Nevertheless, you can solve that, and in particular, you can solve that for the usual harmonic oscillator. And there are a couple of more examples coming. I like this one because it maps closely what we like to do in thermodynamics. So you have an angular frequency that is time dependent. We've used that to model quantum heat engines where the frequency is just 1 over the volume. We know how to do that in BCs, in traps, by just applying the magnetic field. And this is something that we understand well. From a theoretical point of view, what I also very much like about the harmonic oscillators is that linearly, the dynamics is fully analytically solvable. And that's something that we've known since the 50s. And even for nonlinear interactions, this falls within the under the scope of scale invariant problems, meaning that it preserves the symmetry. And using this ansatz, knowing that symmetries are preserved, we can find analytical solutions to pretty much any scenario, any nonlinearity that you can imagine. But I don't want to bore you with ugly hypergeometric functions, so I'm just going to show you a pretty picture. So if we first focus on the first line here. So what I'm plotting is I have the real part, the imaginary part, and the probability density, magnitude squared of the wave function for 3 cases. For the linear case, which means no nonlinearity, it's the blue curve. And then for a medium nonlinearity, kappa is some value, I don't know, 1 or something. And then for a strong nonlinearity, which you see, have in red. So if you first just focus on the blue curve, the blue dashed line, if you start with an initial Gaussian wave packet, it's linear dynamics, which means if you start with a Gaussian, you have Gaussian evolution, you get back a Gaussian. And this is exactly what we see here. It's an harmonic oscillator. No big deal. And you see the same for the imaginary and the real part, but it's proper quantum dynamics, so the imaginary part is non-vanishing. So this is the usual phase that you pick up in the linear dynamics, and it also becomes negative. Now, if you slightly crank up the nonlinear dynamics, then again, you don't have eigenstates anymore, but you still can solve the evolution equation. And if you take exactly the same initial state, what you should see is a different state evolution. And what this does is that here, for the real part, it gets a little bit stunted, so you can squeeze it in a little bit. Same is true for the imaginary part. And for the probability density, it widens a little bit. It spreads out a little bit. And then if you really crank up the nonlinearity and do something crazy, then, well, it's very hard to get any intuition for what is happening. But the wave function does something very, very dramatic, whereas the probability density is still essentially the same. And this is actually a good thing. This is the background of why you can do all of these time of flight experiments. So the quantum cloud is still well contained. It doesn't do anything funky. You don't get any non-uniquely connected probability distribution, something like that. Essentially, this is still a well-defined quantum system. But looking at this difference, what we're now asking is, so this is a snapshot at the end of some time. How quickly does the state become different from the initial state? And this is what the quantum speed limit quantifies, the rate of quantum state evolution. And this is what I'm plotting here. Now, for linear systems, there's no evolution. I started in a Gaussian wave packet. It's an eigenstate. Nothing happens. That's exactly what you would have expected. And then for small nonlinearity, you get this curve. For large nonlinearity, you get this. So it has some structure. It does something. But what we do see is that very much like we expected, the quantum speed limit is larger. So there's a larger quantum state evolution. There's some funky thing going on here for very, very small perturbations, but I don't want to over-analyze that as just something that happens in the dynamics. What I found more interesting was that just looking at these curves, it's not entirely clear that you can formulate simple statements such as the more nonlinear the dynamics, the faster the state evolution. So what I've done is I've taken a crosscut through some value here and computed the quantum speed limit as a function of kappa for keeping everything else constant. And this is what you see here. Right? So quantum speed limit for linear dynamics still doesn't change, right? It doesn't depend on kappa. And then what you see here is that as a value of kappa, positive kappa, it's increasing. And this is good news. So what we find here is that the stronger the nonlinearity, the more bosonic the system. I mean, very hand-wavingly, very loosely speaking, the more bosonic, so the more the nonlinearity comes into play, the faster states can evolve. Okay, now before we start thinking about applications, I mentioned that there are many other ways that we could have derived a nonlinear Schrödinger equation. We could have done different things. We could have included, for instance, 3-body interactions or 4-body interactions. Or in other terms, we could have made the Landau energy a little bit more complicated. Instead of a phi 4, we could have done phi 6, phi 8. So what do you expect? Does it mean that, and this is an example that is pretty well cited in the literature, so this is this Kolomaysky equation, get something that looks very much like the Gross-Perjevsky equation, but you have the fourth power here. So would you expect that if you make the system more nonlinear, and now talking not in terms of strength, but in terms of actual nonlinearity in here, where, you know, the parabola should be still reasonably linear, but then you go to the fourth power, or the sixth power, or eighth power. Does this mean that we necessarily get a higher rate of quantum state evolution, or do we find something different? And again, so this is something that is fully experimentally accessible. You just have to go to a different density regime. And let you think about this for a second before I flash it up. So I was surprised when I found the result. In this particular case, so what I'm plotting again is same color coding as before. So in blue, I have the linear case. In red, I have the strong Gross-Perjevsky case. And in green, I have the Kolomaysky equation. So if you first look at the probability density, we see immediately that there seems to be a more dramatic change in the dynamics, that the probability density is more squished down. We also see that in imaginary and real parts, right? The green curve is much more different from the blue curve than the red curve, loosely speaking. Interestingly, that doesn't mean that the rate of quantum state evolution is higher. So in particular, if you look into this here, so the green curve can be above the red curve, it can touch, can kiss the red curve here, and can go down. Now, what I'm plotting over here is this, again, took a crosscut somewhere here and asked the question, do we at least still see this monotonic behavior? The stronger the nonlinearity in terms of scattering length, do we still see this effective speed of the dynamics? And yeah, you see that here. But at least for this crosscut down here, it seems that the Gross-Perjevsky equation always gives us a larger speed up than the Kolomaysky equation. Okay, not entirely sure what to make of that, but it's at least an interesting statement. Now what I want to do is I want to actually use that for thermodynamic problems. So now that we understand that, that nonlinearity can be exploited, question is, how do we exploit that? And the interesting thing is we have analytically solvable examples in oscillators. What I didn't talk about is you also can solve that for particles and boxes. For particles and boxes, you can even find the stationary states analytically, just more hypergeometric functions, but you can do all of that. But we have very waterproof evidence that these nonlinear speedups exist. Now, what I've found is there's this very non-trivial dependence on the degree of nonlinearity. And by degree, I mean the polynomial order. So one question you could ask immediately is there something like an optimal nonlinearity for which you get the highest speed up? Which could be interesting, for instance, for quantum communication. Like if you take a nonlinear optical fiber, you can control the nonlinearity by bending it. Is there something that you can do optimally to get the fastest state transfer through the fiber? Problem with these systems is, yeah, okay, fibers are no longer harmonic oscillators, which means that you would have to start solving everything numerically, and that's a mess. So I was hoping that we could find maybe simpler, more pedagogical examples that allow me to make analytical predictions, but I also wanted to tie that more into thermodynamics. And this brings me to a paper that Steve was talking about on Monday. Steve told you about the first half of the paper where he spoke about the precision with which temperature can be estimated depending on the energy spacing. He completely ignored the second half of the paper. I think he had the title somewhere on the slide which said precision thermometry and the quantum speed limit. And what we found back there was, well, the quantum speed limit doesn't really tell us much about thermometry. But at the same time, as Diego was saying, we would actually expect there to be a close relationship because the quantum speed limit can be understood as a parameter estimation of time, which is very closely related to thermometry, because in both situations, you're estimating a parameter in the exponent of an exponential. So for linear systems, this was boring. I think this is the only paper that I published in which we have a negative result, where we just said, it's interesting, but there's nothing that we can say. But I wanted to get back to it and now understand, is there something more interesting in nonlinear systems? Exactly because of this problem that I keep mentioning over and over again. Nonlinear systems don't have eigenstates anymore, which means that our thermostate is not necessarily a stationary state anymore, so there should be quantum state evolution. And somehow that has to come into play. This is a beautiful paper from 2016 in which they studied very broadly nonlinear dynamics from the point of view of quantum state discrimination. Quantum state discrimination was directly within quantum speed limits. So they tried to understand how quickly can you tell states apart. What that was, they rewrote nonlinear Schrödinger equations in this form, where you have a potentially time-dependent Hamiltonian, and then some nonlinear operator that does something on this quantum state. If you write it for qubits, and I'm going to use the Bloch representation moving forward, then this nonlinearity here. So this term that goes in here. So this is just expressed now in the Bloch basis. That's why I'm using a curly K. This is a diagonal matrix where on the diagonal matrix you have exactly this nonlinearity that we had before. Right? This can be the Krauss-Petyevsky type of nonlinearity or Kolomeisky. What I find interesting, and this is a plot from this paper here, is to understand what this actually means for the dynamics. So on the Bloch sphere, if you have states evolving, and we've also seen these plots in some of the talks already, usually you just follow some geodesic along, or make this very simple in very simple terms, you're just following down a grand circle somewhere on the Bloch sphere. What these nonlinearities do is that they induce an additional drag around the Bloch sphere. And this is exactly what's shown here in these arrows. So if you have a quantum state that is pointing in the z direction up, and you want to go down to minus z, from +1 to -1, do a bit flip, then usually you would just follow some grand circle and go down here. Because of this nonlinearity, what this dynamic does is that you get this additional drag around the Bloch sphere. And this additional drag around the Bloch sphere, what this leads to is more structure in the quantum states, which means states become much faster distinguishable, which ties directly into what we had seen for quantum speed limits, but now expressed in terms of qubits. Okay, cool. So now that we understand that, let's go back to Steve's example of a simple qubit in a magnetic field and measure the ambient temperature. Before we do that, again, you've seen this already. I just wanted to remind you. So what we need to look at is the quantum Fisher information. More generally, we have to worry about this multi-parameter Cramer-Rao bound, where you have here the quantum Fisher information matrix, which bounds lower bounds the covariance matrix. So don't want to say much about it because you've already seen it. The one thing that I find cool is for qubits, there's a very neat formula for the quantum Fisher information matrix. You know, usually it's a very complicated expression with sums and stuff that you have to do. For qubits, it's not. You just get scalar products of the Bloch vectors. Or in other words, if you know the Bloch vector, you only have to compute the derivatives of the Bloch vector and you know the Fisher information matrix. Makes life much easier. All right, so let's do this for the simplest example that you can imagine. Let's take a simple qubit, spin one half system in a magnetic field. And I think someone asked about the Hamiltonian when Steve gave the talk. This is the Hamiltonian, simplest possible Hamiltonian they can write down. Delta times sigma z. The cool thing about this dynamics is I can solve the nonlinear Schrödinger equation independent of the exact shape of the nonlinearity. I can do that for any k. And these are the solutions for the Bloch vector, right? So you have x, y, and z. These are the Bloch coordinates. The zeros are the initial states. You have the energy splitting in here, and here you have the nonlinear term. And this looks very much like the linear problem. The only thing that changes is that the frequency changes depending on the initial value of z0. Okay, cool. First, I was excited. I have solved the nonlinear Schrödinger equation analytically. And then I was very disappointed. So I want to use that for thermometry. Now, thermometry means that I prepare my system in something that is diagonal in energy. And I'm going to make this precise on the next slide. But what I already see here is this. If the x and y component of my initial state are 0, there's no state evolution. Nothing happens, which means thermostate are perfectly stationary under these nonlinear Schrödinger equations, which means not only am I not going to see any quantum speed up, but I'm also not going to see anything interesting about the quantum Fisher information because it's exactly the same thing. And that's what I'm writing here. So I can write down the quantum speed limit. And again, so this is proportional to x naught squared plus y naught squared. If they are 0, there's no quantum speed limit. It's the stationary state. But then, so the nice thing is this corroborates what I had seen earlier. If I start in a state that is not diagonal in energy, then I again see this quantum speed up. But what I also now see is this is a much simpler problem than I had before. This is already analytical, which means now I don't have to solve the dynamics anymore if I want to find the optimal nonlinearity. But that's more of a side result. The Fisher information matrix also dramatically simplifies here. And it's only dependent on the initial value. The initial value, if these are the thermal weights, okay, we've learned nothing. Well, I still have 11 minutes and 8 slides, so there must be more interesting things to come. So if the simple qubit doesn't work, what do? Well, we go to our favorite qubit, which is Landau-Zener. So Lando-Zener, we have the Hamiltonian here. I can stuff that back into my nonlinear Schrödinger equation, derive the equations of motion, and all of a sudden things become a lot more complicated. So these are these differential equations, and unfortunately there's no way to solve them analytically anymore because now they're truly nonlinear, right? You have these products of the nonlinearity which depends on the value of the ZT, the time-dependent value of the C component times Y and X. But we still can do that numerically. It's very tractable. Now what I need to do is the following. If I want to use it as a thermometer, I need to take the qubit, put that into a thermal environment, let it equilibrate with, which means I prepare a Gibbs state, and then I need to estimate the parameter temperature, or I need to estimate the precision with which I can say something about the temperature of the ambient. So this is the Gibbs state, just now written in Gibbs in block representation. And I wrote it down because it's maybe not something that we usually write down, but this is just the Bloch vector of the Gibbs state. But you can read off directly the initial conditions. So you have a differential equation, you solve that, and this is what you get. So on the left-hand side, again, Gross-Petrajewski nonlinearity. In red, again, the linear case. In purple, some slight nonlinearity. And in blue, some strong nonlinearity. And what we see is, as before, the nonlinearity leads to a speed up in quantum speed limit. Okay, great, cool. If I do that for another nonlinearity, and I like this one because it's not as common in the literature, so there's a logarithm of x squared. This is something that you would find for both liquids, an effective description of not both gases, but both liquids. The speed up is even more dramatic. What I also find interesting is that we still find these very regular oscillations. Okay, so speed limit goes up. Speed limit, at least linearly, should be related to quantum state discrimination and thermometry. So you would expect the Fisher information also to go up because the state becomes more distinguishable more quickly because of this additional drag force. And that's exactly what you find. So the Fisher information, and here I'm only plotting the temperature component, so it's a Fisher information matrix. You can compute, strictly speaking, you have 3 independent parameters. It's non-singular. But I only plotted the temperature because this is what we really care about here in this problem. In the linear case, this is the Fisher information. In the linear case, the thermostat is stationary, so the Fisher information doesn't change. But for the nonlinear dynamics, the thermostat is non-stationary, so it starts flopping around. And then for a mild nonlinearity, you get this purple curve. And for a strong nonlinearity, the Fisher information shows this dramatic increase. And for both liquids, this becomes even more dramatic. Okay, so what we've seen here is, on the one hand, it's very intuitive and expected, but on the other hand, it's also really cool. We've seen that nonlinearities can be exploited in quantum metrology because states that are usually stationary are no longer stationary under nonlinear dynamics. So states become more quickly, more distinguishable, and that gives us additional information. But wait a second. If states are not stationary under the nonlinear dynamics, how exactly are we going to build a thermometer for the ambient temperature out of a Lando-Zener model? So what I said was, so what you usually do is you take the qubit, you let it equilibrate with the environment, and then you measure. But how do you equilibrate if the state is not stationary? How do you actually get there? So this is interesting, but it's probably not a good model for thermometry. But luckily, our old paper comes to the rescue, because although back then we didn't really like it, and we came up with a very simple model of a thermometer. Let's say you have one system that is prepared in a thermostat, and then you stick your thermometer in, you let it interact, and you measure on the thermometer, or you literally do what you do whenever you measure the temperature of anything, right? You have a system that you want to measure, you have a thermometer, you stick it in, and then you read off whatever the thermometer tells you. In the simplest case, you take again the simple Hamiltonian that we had before, spin 1/2 particles. You do something like a swap interaction, very simple coupling term, where you have some excitations initially in the system that you want to measure. You wait until the excitation swaps over, and then you measure on the thermometer. And the only thing that I'm now going to change is I'm going to make the thermometer nonlinear. And this is not particularly crazy, so I could use a thermometer that has a BEC phase transition, which undergoes nonlinear dynamics. And funnily enough, mercury in glass thermometers would do exactly that. So if you want to use mercury in glass thermometers below 4 Kelvin, this is essentially what you're looking at here. Now what I need to do is I need to solve the dynamics. It gets a little bit ugly because now I have these 16 parameters that I have to solve. Still can write down the equations of motion for that. The initial state is obviously a product state. They're prepared independently, and then I just link them together. Okay, what do you think? Do we still get a quantum speed up? No. Now the quantum speed limit for the nonlinear dynamics actually goes down. And this is something that is pretty easy to understand. So what we're now looking at are two coupled systems. Think of two coupled harmonic oscillators. So what you usually do is this. So I don't know, physics 101, it's one of these mechanics labs that everyone has to do. So you have a harmonic oscillator, a pendulum, that you couple with a spring to a second pendulum. If one is oscillating in the beginning, then the swap interaction, so the spring does nothing else but swap the energy over there, and the first one stands still, so this one starts oscillating, and then it goes back and forth. Now, what does this nonlinearity do? This nonlinearity introduces an additional drag around the Bloch sphere, which in my simple example here means that we have an additional torsion around the z-axis. And this additional torsion around the z-axis, this is an additional drag force that prevents the transmission of energy from one oscillator to another, which means the rate of quantum state evolution has to go down. And that's exactly what we're seeing here. And as before, this is again more striking for the more interesting case. However, additional drag force means more structure. More structure means states become more distinguishable. So the quantum Fisher information still should go up. And it does. And this is exactly what you see here. And again, in the same color coding. So in red, you see the happy bumping back and forth of the Fisher information for the linear case. And then for the nonlinear case, this quantum Fisher information. So the peak is a little bit delayed. Quantum speed limit is slower. So it takes a little bit longer for the excitation to go over. But then you get this dramatic improvement here, orders of magnitude improvement in the quantum Fisher information. All right, so this is all I wanted to tell you today. So I think nonlinear systems are interesting from a quantum thermodynamic point of view because they have a lot of resources that we haven't really tapped into yet. There's a lot that we haven't really studied. There's another paper that I haven't spoken about in which we use BECs as a working medium for a heat engine. And we found results that are very consistent with what we have here. Nonlinear effects are additional resources that we can exploit. There's an entire zoo of things that we can solve analytically. And generally, up to these coupled systems, we find that quantum speed can be boosted. And it also means that the quantum Fisher information can be enhanced as long as the state that we want to measure is non-stationary. If it's stationary, then the nonlinearity doesn't help. Okay, and then before I conclude, I'm contractually obligated to mention, yes, we have a graduate school. We're looking for graduate students. So if you know of someone who wants to come to Baltimore and do a PhD, let me know. Thank you.
Thank you, Sebastian, for the nice talk. Questions?
Well, thanks for this beautiful talk. Can you go again on the slide on which you saw the different Gross-Pitaevsky equation? You know, the one with the normal one and the one with the higher power exponent? Yeah, so this is very surprising. It means that if you have a stronger nonlinearity, then you have a slower speed limit, or if I understood well?
So this is for two examples. And I would like to be able to make more general statements, but I can't for these systems because it would require going through everything on nonlinearity and numerically. What I would like to do is I actually would like to phrase it as an optimal control problem. Choose this exponent as a free parameter, and then solve for the optimal nonlinearity such that we get the highest speed limit. But that's numerically very, very expensive, which is why I first looked at these problems here. Because in these problems, in particular for the simple spin model here, the quantum speed limit can be written analytically as a function of this nonlinearity. And in this case, it doesn't become an optimal control problem anymore. It's just an optimization problem. But I haven't done that yet.
Okay, and on the other slide, with the red and green curve, yeah, it really seems that at any point, you know, the green curve is below it. It saturates sometimes, you know, it meets the red curve, but it's always below. So it's just an example, but there is no. Do you have a general intuition on why is that? Or?
So it looks as if it was saturating, because the slope becomes very, very small, but it's actually going down. So it's doing something like this here. So it's going up, down, and then up and down, but the period of oscillation has become longer and longer. I don't have a good intuition for what exactly the dynamics is doing in the long time limit. But I wouldn't expect it to be stationary, so I wouldn't expect that to saturate.
Okay, well, thank you very much again.
I can hear you.
Thanks for the talk. So I mean, I've become really interested in this sort of classical speed limits recently. So I mean, as you know, like Fisher information is well-defined classical concept on the space of probability distributions. So I was wondering, like in Gross-Podolsky theory, usually, right? Like, so in practice, I mean, there is this Thomas Fermi approximation that you can do, which is essentially amounts to neglected kinetic energy, and it's kind of used often in practice. So there you have the ability, at least in a certain regime, to kind of solve for the density dynamics as a function of time, right? So I mean, what I'm wondering is that then you can really define classical Fisher information on the density of the actual condensate. Right. And do you have any intuition, like, would that give you the same stuff as if, you know, you just did this sort of procedure on? Because for me, it seems kind of funny to apply the quantum formalism to the Gross-Podolsky, because the Gross-Podolsky kind of mean field equation or something already quite classical.
So, okay, I don't think that what I'm doing here is fully quantum, in the sense that the way that I'm defining the speed limits is really just given as the rate of quantum state evolution. So if we're going back all the way to here, so this is actually a classical speed limit. This is the speed limit of the rate with which the probability distribution in position changes. All of that should carry over to the classical limit whenever you do this Thomas Fermi approximation. One thing that I haven't done yet for this system is, but for other systems, a couple of years ago, I looked into what happens to speed limits, this type of speed limits, if you have open system dynamics. So I don't like classical limits where you just set h bar to 0. Doesn't tell me all that much. But what I did was I looked into open system dynamics for which you can compute the quantum speed limit for something like quantum Brownian motion, and then computed the quantum speed limit as a function of temperature. While also for higher temperatures, the classical speed limit is fully well-defined. What you do see is that the classical speed limit, the rate of state evolution, goes up, which is consistent with uncertainty principles not really playing a role anymore. Now, if you ask me about intuition, I would expect something similar here, that if I plotted speed limits as a function of temperature, that for high temperatures, the rate should go down. But honestly, I don't have all that much solid intuition for these nonlinear dynamics that I want to bet on it.
Yeah,
but it's something that we should look into.
Yeah, and maybe just another comment to this Komolsky thing, because I remember it from my PhD days, believe it or not. But I think it was basically that thing was designed for modeling 1D gases, right? So you can typically write down mean field theory for 1D, but they said, okay, let's add a higher nonlinearity and see if it works for the density, but not for momentum. That's the problem, right? So just wondering if you thought about like anything in momentum space as well, because like momentum space is kind of the key for thermometry in standard BECs, like, right?
Not here yet.
Okay.
But yeah, I circumvented the problem by going to this very simple representation, and then I'm writing it for qubits, and then I don't worry about that anymore. But yeah, I looked into momentum and I realized, oh, that's complicated. I don't understand what this is.
So did you study the case in which you are away from a mean field? So is this trend that you see, the increased speed limit, is just related to the interaction between particles, I understand, between bosons? So do you see it also away from mean field?
The honest answer is I have no idea, because I haven't looked into it yet, but it's one of the things that we should do. We went away from mean field for the heat engine. For that, it was actually quite crucial, but we haven't done that yet for the speed limits.
A very interesting talk. I have a lot of questions, so I'll try to stick to only one.
We have time.
Well, but she has questions too. So we have some analogy between the Kramer-Rao bound and quantum speed limits. Is there an analogy between the multi-parameter version of the Kramer-Rao bound and, I don't know, maybe many time scales quantum speed limits or something like that?
That question I would like to defer to Steve, who made me look into multi-parametric Kramer-Rao. I don't know.
Okay. Perfect. Okay.
Thank you for the talk, very interesting. About the parametric oscillator is somewhat a pathological system, and you have these parametric resonances. So I was wondering if these peaks you see were kind of signature of parametric resonances. I don't remember the sequence of the resonances. That was one of the part of the question. The second,
To answer this question, I think so.
Okay.
But these peaks also show up for a parametric box. So you take a particle in a box and you increase the volume. I didn't show the plots here because they're essentially identical to what I've shown, and you also see these peaks. So I do think that there's these parametric resonances here.
Okay.
Or effectively conserved adiabatic invariance or something like that.
Yeah, okay, thank you. The second part was following this. I mean, again, it's a bit of a pathological example because your state basically wants to ionize and it cannot because you have this infinite potential. So I was wondering if you have tried to put in some anharmonicity to see if this, because you have this great increase in the quantum speed limit. I wonder if some anharmonicity would, how would that correct, if it would correct it dramatically, because you take off all this degeneracy of your...
So I haven't done some anharmonicity. I just went to the other extreme. I went to the infinite box and the structure just, it survived. So I didn't really see much interest in going somewhere in between, but maybe there's something interesting. I think what comes more into play here is that the problem remains scale invariant. So you need to break internal symmetries.
Thank you.
Well, we're going to have just one more question, and then we're going to move to the next speaker.
Thank you very much it was a great talk. Lots of questions. We'll certainly talk later, but I was wondering, maybe it's half a question, half a provocation or something. Because for BECs, as you well said, this is one particular example in actually for experiments where a simple model actually works pretty well for representing the physical system, but it's nevertheless an approximation. Of course, it's a simplification of a many-body problem. And for BECs, the context where Grosbeck effects apply is actually the zero temperature limit. I mean, it's essentially describes a system which has zero temperature. So it's kind of funny to think of it to measure temperature. But of course, this system actually interacts with a cloud called a classical cloud, a thermal cloud, and has finite temperature. So I wonder if you want to look into something, or descriptions that do the extension of the Grosbeck equation at finite temperatures. Usually you connect to the classical fields and approximation like this.
So I agree with everything that you said. For speed limits, we haven't done yet because first we need to do the groundwork. But for the heat engine, as I was mentioning, it was very, very essential to work with fundamental relations, equations of state that take into account the thermal cloud.
Okay, we'll talk more later. Thanks very much.
Well, let's thank the speaker again. Well, the next speaker is Giorgio from Belfast. Giorgio, the floor is yours.
Thank you very much. Thank you to the organizers for having me here. Thank you, Taisa, for organizing this. I know you put a lot of effort in organizing all this. Thank you. So today I'm going to talk about spontaneous collapse models. Actually, we had a talk by Mauro on Tuesday, was more talking about the thermodynamic implication of those models and some of the inconsistencies that arise. Whereas today I'm going to talk about the estimation of the collapse rate, which appear in that kind of equations. So I'm going to talk about essentially quantum metrology, or at least, I mean, that is very ambitious. I'm going to talk about the way we estimate the collapse parameter. So first of all, let me start from an outline of this talk. So first of all, I will introduce collapse models. At least I will stress a little bit on some points that maybe were not covered by Mauro. And then I will go to, I want to introduce some of the tools we need for this analysis, which are basically provided by quantum estimation theory. And then I'll go back to collapse models to see how that can help for estimating the collapse rate. Right. So first of all, let's start from scratch. So we are talking about the quantum to classical transition because we know that quantum mechanics scores pretty well for describing the macroscopic world, whereas we have classical laws that are needed for describing the physics of macroscopic objects. So the question there is the following. So the question is, how does the quantum to classical transition happen? Because we know that, I mean, in quantum mechanics, you can have, for example, spatial superposition of states, whereas you cannot have superposition of, spatial superposition in macroscopic objects. So essentially, we want to discuss how this happens whenever we consider bigger and bigger objects. So we start from very small objects to macroscopic objects there. So the question is kind of related to one of the first thing we all learn in the first module of quantum mechanics, which is duality of the evolution in quantum mechanics, in the sense that we have a Schrödinger equation. So whenever we have a system which is fully described by a state psi, then the evolution is governed by the Schrödinger equation. Whereas if we perform a measurement, then we have the collapse of the wave function. So this is, in the context of measurements, but the question there is, so what does this, so the Schrödinger equation is something that is deterministic and linear, whereas in this case is the problem is stochastic and nonlinear in the sense that we need to renormalize the wave function, and of course this is associated to a certain probability. So the question there is, what if the wave function spontaneously collapses? And that is kind of this is the main topic of this kind of models. The first attempt was made by Ghirardi, Rimini, Weber in this model that dates back to 1986. So basically, we have a certain system which is fully described by a wave function psi t, and then we have a sudden jump which happens in position space. And the reason why this happens in the position space is related to the fact that the physical intuition that macroscopic objects are well localized in space. And then the other question is, when does this collapse happens? And in the GRW model, this happens with a discrete stochastic process, which is the Poisson process, with a certain frequency that is given by lambda. And then how does it happen? Basically, this is an application of what we saw before. So we are applying a certain operator here, which is the localization operator, which is a Gaussian. I don't know why. Okay, a Gaussian. And we apply that to the initial wave function. Then the evolution between jumps is given by the Schrödinger equation. And the other thing I want to stress here is that this model introduces two physical constants. One is the frequency with which the collapse happens, and the other one is the coherence length, the critical length RC, which is the length at which the superposition principle breaks down. They also propose a numerical value, heuristically they propose a numerical value for that in this seminal paper here. So, but the question is, how can we embed the collapse in the dynamical equations in a continuous way? The answer comes from this model, the continuous spontaneous localization model, which essentially does the following. So we need some sort of constraints to generalize our Schrödinger equation, which means that we need nonlinearity because we want to break the superposition principle at a macroscopic level. It must be stochastic because we need to recover the quantum indeterminacy. And we also need some sort of amplification mechanism, because as long as we consider larger and larger objects, then we need, then the collapse should more likely to, should be it would be more likely to happen, right? And then, of course, the minimal requirement is that we need to comply with special relativity. So at the end, we had this. If we blend carefully all these ingredients, then we have a non-linear stochastic Schrödinger equation where we have the localization rate here. Then a Wiener process. This is a stochastic Schrödinger equation. So we need some sort of stochastic process, which is the Wiener process in this case. And then we also need a collapse operator, which is there, that A, which is a self-adjoint operator that governs the collapse in this continuous setting. Right. So let's move on. So I'm not a quantum foundation guy at all. So maybe I can rephrase this problem in a different way, which is more maybe closer to what it has been discussed in this workshop. So essentially, we have this picture here. We have a certain quantum system. This system is fully described by a density matrix at initial time. So we consider general states, also mixed states. And then this system undergoes a certain dynamics. So let us suppose that if the system is quite isolated in the ideal scenario, we have this Von-Neumann equation, which is the equivalent of the Schrödinger equation. That is coherent, preserves the purity, so on and so forth. But if we think, as we always do in quantum thermodynamics, that our system is coupled to an external buff, whatever it is, so it could be a thermal buff, a non-equilibrium buff, whatever. So we have a master equation, which in the Markovian case looks like a Lindblad equation. So in that case, you have other phenomena that were not encompassed in the previous case. So the question in this framework is the following. So can we formally use the formalism of open quantum systems to describe something that is happening fundamentally in enclosed quantum systems, such as the collapse? So the idea is that we can describe the collapse happening in an isolated system as a noise field which is non-linearly coupled to any massive object. This is what it's basically the idea that is behind this. Maybe this answers to a question that was that someone arose. A couple of days ago. So basically, this is not an external buff. We can see it as an external buff, but the effects are very tiny. So for macroscopic objects, you are not going to see anything. Right. So just to make this connection closer, we start from this equation, which is a nonlinear stochastic equation. Then we use the Ito calculus to rewrite that equation in a form of a master equation. And as you can see, this is a master equation in the Lindblad form, where the Lindblad operators are self-adjoint, right? Then in these models, we basically introduce different natural constants. So for the GRW model, the constants are the following, so lambda and RC, whereas in the CSL model, they are kind of related one to the other. But since if we fix RC, basically that boils down to the collapse rate. So that is the plot that Mauro was also showing a couple of days ago. So we have these exclusion plots that excluded those regions where basically we cannot find any value compatible with the collapse. So the only region left is this small region in white here, whereas those are theoretically excluded by the fact that we cannot basically observe quantum superposition at the macroscopic scale. So now the question is the following, which is what my work is about. So the theoretical question to be addressed is the following. How can we obtain the best estimate of the collapse rate? And that turns out to be a simple, for a quantum estimation problem, right? So let me just briefly talk about this. So Steve covered most of these things. And I think he was saying, so he said that these problems come in 3 different flavors. He talked about the third one. I'm going to talk about the first 2. So basically, we have already a critical system, and we want to exploit the criticality, which is, kind of boring in that sense, right? So let's start from scratch. So essentially, when we want to estimate a parameter in the classical setting, we want to estimate a certain lambda. This lambda cannot be measured directly. So that comes through a certain classical observable X, and we want to perform a certain, we gather a certain sample, and we build an estimator with that. So whenever we have that data set, that is basically, from a probabilistic point of view, a set of random variables which are distributed according to a certain probability distribution, which is the likelihood function. The question, the basic question there is, how much information does this data set contain about the parameter lambda? And we can look at the logarithm of the likelihood function. And as you can see, so the steeper the tangent, the more informative is the probability distribution, which means that our curve is peaked around a certain value. So that inspires the definition of the Fisher information and also enter in the ultimate bound with which we can estimate the parameter lambda, which is the Kramer-Rao bound. So essentially, we have that the variance associated with the parameter lambda is greater or equal than 1 over m, where m is the number of independent measurements, times the classical Fisher information. Then if we go to quantum, this is a little bit trickier, because then we need to estimate a parameter lambda through a certain observable O, which is built as, for example, as a trace of some state rho that depends on lambda. Right. We define the quantum Fisher information. This is basically the definition. And we can also find a quantum version of the Kramer-Rao bound, which is the following, and which comes from the fact that the classical Fisher information is upper bound by the quantum one. Then, just to give you an example, let us consider, which is actually useful for what follows. So let us suppose we have a certain qubit. We want to calculate the quantum Fisher information. We can decompose our density matrix in that way, and then we can calculate, using the definition up there, the quantum Fisher information. This is the classical part, where you have basically a trivial probability distribution with the two eigenvalues, and then you have the derivative of the eigenvectors that account for the quantum part, right? Now, the part that is important for my work is about criticality, in the sense that it's well known that whenever you want to estimate Hamiltonian parameters, quantum criticality is somehow resourceful for that, in the sense that it amplifies our ability to discriminate the parameter we want to estimate. So let us suppose we have a certain quantumizing model at zero temperature. So the quantumizing model, has its Hamiltonian, it's like this. And we know that this can be exactly solved, and h equal to j represents the critical point. So if we want to calculate the quantum Fisher information, whenever we want to estimate one of the Hamiltonian parameters, either h of j or j, so the local feeds or the coupling between the spins, you can calculate the quantum Fisher information also for small values of n. You can do it analytically. And what you find out is that even for small values of n, you will end up having this kind of behavior, in the sense that h equal to j maximizes the quantum Fisher information. So you don't need to go to the thermodynamic limit. And this holds true also in the thermodynamic limit. Right. Then we want to use this to probe our system that is undergoing the collapse. So for doing this, we have some sort of equilibrium approach or a non-equilibrium approach. Essentially, in the equilibrium approach, we are deducing the property of the system by looking at a specific state. This is what Steve maybe was referring to. And then in the examples about thermometry. And then there is the non-equilibrium approach, which is a sort of dynamic encoding, in the sense that we dynamically deduce the properties of the system through a fully controllable probe. So just to give you an example, which is maybe more familiar for the audience, this is about thermometry. So the picture here is that we have a pie, and we measure the temperature when the pie is ready. Whereas in the non-equilibrium approach, we are measuring the temperature while we are baking the pie. So that is a non-equilibrium, the dynamic encoding of the information. So if we consider, for example, a quantum thermometer in the simplest possible case, so a two-level system, what we do is to estimate the temperature T, and we want to calculate the quantum Fisher information. That was basically what Steve showed a couple of days ago for several levels, but I mean, this is for just for a qubit. Then in the non-equilibrium approach, you attach your probe, you initialize your system in maybe in a product state. So your system is in a thermal state, and then you have your probe, which is, for example, in a pure state. Then you let them evolve, and you trace out the system, and you calculate the quantum Fisher information by looking at the probe. And you get something similar. Of course, it's smaller than that. Okay, let's go back to collapse models. So that was just to use some of the tools of quantum estimation theory. So our aim is to estimate the collapse rate. So let's start from the simplest non-trivial example, which is the qubit case. We have a single qubit, and we encode two spatial configurations here and there in plus and minus or up and down. Right. The nonlinear stochastic equation reads like this. We can write it down, as I said before, in a Limblad form, which is very simple. So that makes me happy. And this is the unitary part, which is in sigma x. And then there is a dissipator, which accounts for, I mean, it's a decoherence-like term in sigma z. Right. Then we want to, our aim is to estimate the collapse rate here, lambda. So if we solve the dynamics, and this is very trivial for a qubit, we can write down our density matrix in the block form, and we can monitor basically what happens to the components of the block vector. But what we find out is that if we start, for example, from I mean, whatever initial state, then we end up at the center of the block sphere, which means that our steady state is a totally mixed state. And this implies that we cannot measure, I mean, we cannot estimate, we cannot do any kind of estimation of the parameter lambda just by looking at the steady state. We should dynamically encode the information. So what we do is to take our system, which is locally undergoing the collapse, which is given by this dissipator here, and we attach a probe here in this way here. So this is the coupling parameter, and those are the Hamiltonian that refers to the system and the probe only. Right. So we solve the dynamics, which is, I mean, intrinsically open because the system is undergoing the collapse. And we trace out the system. Once we trace out the system, we can compute with the formula I was showing before, the quantum Fisher information. And that is the quantum Fisher information for just one, for one qubit. And of course, we need to plot the signal to noise ratio just to see how that compares to the variance of lambda, right? But if we move to a many body setting or few body settings, we can actually think a certain array of qubits individually and independently undergoing the collapse, which are there, and then we attach a probe to the very last qubit. We are working in open boundary conditions, right? The Hamiltonian is very similar to the previous one, where the system is given by the Ising Hamiltonian, and then we have a similar coupling with a different coupling strength with the probe that is at the very end of the chain. We solve the dynamics, which is given by this sum of some incoherent sum of dissipators. So you have individual dissipator acting on a single particle, and we trace out the system, and we see what we calculate the Fisher information. So essentially, what we are doing here is that we take all the possible values of lambda, which are the following. So they can be whatever, I mean, depending on the model you are considering. And then you consider different system size. We are considering small sizes because those are the one that you can simulate very easily. I mean, just by exact diagonalization. And then we consider different J over H ratio, which measures how far we are from the critical point, or the theoretical critical point, I would say. So, for example, if we consider a small chain of 4 sites here, we still see that H equal to J, which is the theoretical critical point, helps us in estimating the parameter lambda. So essentially, also for even for small systems, quantum criticality enhances our ability to discriminate the collapse, the collapse rate lambda, right? What happens if we consider, different size and for j equal to h? So we're working at the theoretical critical point. So for example, if we consider this interval here and we calculate the quantum Fisher information or the signal to noise ratio, we realize that actually there is always an advantage in working at the critical point, but we don't know if for such small systems for this small system, there is no monotonic behavior with respect to the system size. If we work, for example, in a different interval here, so we still have a non-monotonic behavior, which essentially in this proof of principles, we show that there is no monotonicity behavior. Maybe you need to go to larger system, but still, even when you consider small systems, you are able to exploit criticality to estimate the collapse rate. Let me go to the conclusions. So we use a non-equilibrium of dynamical encoding on the information for a model of spontaneous collapse, which was basically the CSL model. We discussed the possibility of enhance our ability to discriminate the parameter, the collapse rate, just by using a few or many body settings. But the role of the system size is still unclear, at least. We need more sophisticated technique to simulate the system if we want to have a scaling law for that. And with this, I thank my collaborators. So I did this in collaboration with Matteo Carlesso, who is the expert about collapse models, Andrea Trombettoni and Mauro Paternostro. So Carlesso and Trombettoni in Trieste, and Mauro Paternostro in between Belfast and Palermo. So that is the reference, and I thank you all for your attention.
No questions?
Yes, can you? Okay. So we recently published this work where we tried, we basically estimate the time of the collapse in a Zurichian framework, so in this, say, standard framework, using quantum speed limits. And we conjectured that we could apply to exactly to falsify the standard Schrödinger approach and maybe apply to spontaneous collapse model. And I wonder if we could use something like this here, like use Fisher information, and like it's a similar approach somehow to quantum speed limits.
So my answer is, I don't know.
Okay, maybe we can chat later.
Yeah, we can chat.
Okay, thanks.
So I apologize. The question that I'm going to ask you, I actually wanted to ask Mauro, but then I didn't get a chance.
Yeah.
But I think it's still interesting. And the question is, so when you write down your stochastic Schrödinger equation, you need to assume something about your noise characteristic, and you write down a Wiener process. I strongly suspect that most of your results will depend on the specific noise characteristics, or rather the distribution of the fluctuations. Is that something that people have looked into?
I don't think so. I don't think they look at that. But the point is that, all we are considering here are stochastic average. So you don't see, at the end, you are averaging over, a stochastic ensemble. So you don't see.
Right. But
So we are not using the stochastic Schrödinger equation. This is what I mean.
Right. But you derive a master equation from that, and the diffusion term usually is correct. So the effective diffusion term in your master equation comes from, for the lack of a better word, the fluctuation dissipation theorem for the stochastic Schrödinger equation.
Yeah, I actually don't know if people have looked into this. Also, because there's the other problem that Mauro was mentioning, that all these models are a bit inconsistent in terms of thermodynamics. So people have been trying to modify those, but until they don't find a solution to that problem, I don't think they will, they have answer in that respect, I guess.
Okay, interesting.
Thanks.
Any more question? No? Okay, Giorgio, very nice. Just
curiosity. So whenever you have your chain and then you have them coupled to their like local baths, how, first of all, how like well motivated is that as an assumption? And then like what happens if I were to assume that like my chain of 4 or 5 or 6 spins or something were sitting in a collective bath? Do you still expect that the criticality will still give you enhancement, or will everything fall apart?
Okay, that is a good question, actually. So I think it's well motivated in the sense that we assume that the collapse acts independently on each particle. But then regarding to the bath, so the point is that all these kind of dissipators acts, I mean, the rate is very, very small. And we checked that actually. So if we consider correlated bath, so correlated noise, you don't get any advantage in the sense that any difference in the results. So basically you get the same result in terms of quantum Fisher information. So that's why we thought, okay, we can assume that they are completely independent and there is no correlated noise. But I mean, that is a good point actually. We looked into that. Thanks.
I mean, this is also kind of a curiosity question. Have you talked to experimentalists and got any data that actually limit the value of lambda from?
No, we haven't. I mean, we are in touch with them. No, I mean, we haven't. But I mean, there are several experiments where they try to test, I mean, which is basically the plot I was showing before, those exclusion plots. Those are all experiments. Yeah. Usually, I mean, for example, they do, I mean, experiment in I mean, optomechanics or whatever, where you have a very high precision for testing the consequences of these collapse models. Of course, you can. So the point is that in principle, the most trivial way to test this would be to take 2 macroscopic objects and then test directly the superposition of them, and when it breaks down. Of course, that is very difficult to perform as an experiment. So usually what people do is to study the Brownian motion of a particle, and that can be done in several experiments. So it's just I mean, and they test it indirectly, not somehow. Yeah, but I mean, the point is that this is a proof of principle in the sense that we just explore how I mean, our ability to discriminate lambda is enhanced by the criticality as well. Thanks. Saru.
It's just related to the last thing you said. But when you have 2 masses, I guess you also have Casimir forces, which are there. So is it possible to distinguish between this? I mean, do you know? I mean, I'm just curious since you mentioned.
I don't know if yeah, maybe this is related to what I said before. So essentially, I don't know if you can compare them. The point is that all those effects are very, very tiny, and I think so the whole point is to try to isolate this effect with respect to all the others. So I don't know. I guess I don't know if you can distinguish them actually. So yeah, I don't know.
Any more questions? No? So let's thank Giorgio and all the speakers of the morning session. We are now closing the morning section of the conference, and then we'll come back 2:15 for the afternoon section. Have a nice lunch.
So should
Afternoon. Let's start the afternoon session of the conference. So welcome back. And the first speaker of the afternoon is Gerardo Adesso from Nottingham. The floor is yours.
Thank you very much. Thanks everyone for coming back. Yeah, I see that you're all taking pictures of Guillermo here. Right, so this talk was done mainly by him. You probably know him. He's a student with Diogo, and I have rented him for a year, thanks to FAPESP. So yeah, so this is, I think, the most we could come up with for a talk which is at the intersection between quantum information and thermodynamics, and I hope that this will be of interest to many of you. I mean, for all the other speakers have already kind of pointed out where they are on the map. So in case you don't know, well, I've heard my name mentioned several times during the week for previous works to thermometry, continuous variables, speed limits, and so on. But for those of you who don't know me, then I am from Nottingham. Well, I'm Italian, but I'm based in Nottingham since 16 years. So finally I have a dual British citizenship as well. Nottingham is in the middle of the UK. Okay. Yeah. And what do we have? We have a very nice student city. I think it's the one with the most independent food and drink places in the UK. And then we have Robin Hood. That's it. So if you are interested to come and study and work with us, we are launching a new master program, which is now recruiting. So if some students here want to do a master in the UK, or your students that are not here want to apply, consider this. And there's another thing. Usually you do these announcements at the end, but I want to do the one on the right now, just because there's a conference we're organizing in Germany in February on quantum metrology, multi-parameter quantum metrology. But the application deadline is today. So if you are interested, stop following my talk and then go to this webpage and send in some contribution. Then we will review it next week. So I think this is enough as an introduction. So let's just actually go into the talk. Now, this is a conference on quantum thermodynamics, quantum information. And quite surprisingly, we've heard, well, not surprising. So this is a field which connects very different communities, right? That's why we all like it. And there's a lot of previous work that is now bridging into quantum thermo from the open quantum systems community. But then there's also, from the quantum information side, one way in which we are, oh, okay, I get free time. So one way in which we are approaching this is to characterize thermodynamics as a resource theory. Okay, so what I was saying about surprising is, so far we are now into the almost final day of the conference, but I don't think there have been talks that much into the resource theoretic side of quantum thermodynamics. So I'm going to give a very brief mini tutorial on this aspect, because this is the aspect that we take in our work. So the idea of a resource theory, for those of you who are maybe more interested from the quantum information perspective, I think it was originally motivated by thermodynamics, but then we developed a lot of it for entanglement, coherence, and so on, and then we are now coming back somehow to thermodynamics, especially in the quantum regime. The idea is that somehow you have, okay, so we can have a metaphor, right? So we inherit from a long-term relative that you never knew, some basement full of equipment. It could be a new lab like here, or you don't know what it does. So this is given to you for free. And then what you do, you start experimenting with this equipment, and then you realize that if you use certain inputs, then you might obtain some useful effect. Otherwise, you might not. So this is just a metaphor for the way we typically characterize resource theories for quantum states in terms of classifying states which give some useful effect, which possess the resource that we care about, and states which do not. The states which do not, we call them free states. And similarly, we can classify quantum operations into free or non-free. Usually, this characterization comes from physical constraints. Okay, so for instance, if you think about what you're allowed to do in a certain paradigm, those are the operations that you can implement for free. And what would require you to consume resource in order to implement, these will be non-free operations. So the idea is that once you establish this kind of framework, identify what is useful, what is not, is a little bit of discrimination at the level of quantum states, unfortunately, but it allows us to appreciate what we cannot get for free as something which gives us a potential advantage in applications, which can range from quantum computing, quantum metrology, quantum communication, quantum thermodynamics, and so on. So if you want examples to understand this little distinction here, I think the most developed, the most famous one is actually entanglement theory. So in entanglement theory, we have a physical paradigm. So say for bipartite entanglement, we have Alice and Bob who live, one in Brazil, one in Nottingham, let's say, and they can only operate by locally applying transformations to their part of the system and then communicate classically. This is what we assume is free in entanglement theory. So our free operations would be local operations and classical communications, often abbreviated as LOCC. And so then you can immediately understand which states are free and which states are useful. So the useful ones, the ones that you cannot get for free, they would be the entangled states. Because all the states that you can obtain just by implementing local operations and classical communications, they take this form. No? So they are convex mixtures of tensor product states, one for A and one for B. And these are separable states. They do not contain any entanglement. Anything which cannot be obtained this way will be useful. It's entangled. And we have plenty of applications of entanglement. I don't have to list them here. And then these questions that you can address with a resource theoretic framework is, for instance, what is allowed and what is not allowed in terms of manipulating quantum states under free operations alone. Okay? So one of the questions is, for instance, very easily and well established for pure states. If you want to go from one pure state, bipartite, to another pure state, then you can do this if and only if certain conditions on the local spectrum of the density operators, which involve majorization, are satisfied. And if you think of it, this is a kind of no-go result, right? So certain transformations are not possible, like thermodynamics would tell us in different conditions, okay? And on the other hand, you can quantify the amount of useful resource, in this case, entanglement, for the states which have some non-zero resource. And there are some important requirements that every measure of your resource has to satisfy. The most important one is it has to be monotonic under those free operations, non-increasing. So free operations cannot create your resource, but can also not increase the content of resource in a state that is non-free. Okay, and so if you try to do some transformation physical operation which would violate monotonicity of certain measure, then that transformation would not be allowed. So you can get no-go results by looking at monotonicity and how it's respected, and you can get quantifiers of your useful resources by imposing that they have to be monotonic under your free operations. How do we take this paradigm back to thermodynamics? Well, I think this is not new. This has been done. There are various approaches. I'm going to follow one of the most common ones, which connects thermodynamics with resource theory of being out of thermal equilibrium. And why? Because basically this is a way of formalizing the basic laws of thermodynamics. So let us just remind us these laws. We have a zero law that somehow establishes the concept of temperature. If A is in thermal equilibrium with B and B is in thermal equilibrium with C, then A is in thermal equilibrium with C. So it defines thermal states and tells us that the equilibration is a transitive property. Then the other laws, first law is about conservation of energy. Second law, you can formulate it any way you want. If you want, I don't know, the entropy of a closed system cannot decrease. And then the third law, which we will not consider that much, is about, you can also characterize it as a resource theoretic, it's a derived law somehow. It tells you that if you want to cool some system to the absolute zero, then this requires infinite resources, say infinite time or infinite resources in a way or another. We will formalize the first three laws in a sense of characterizing what is useful and what is not for thermodynamic purposes. And what is the thermodynamic purpose that we mainly care about is extracting work from quantum systems. Because with this work, you can charge batteries, as we've heard a lot this week. You can power steam engines, you can do whatever you like, okay? That's the main task. Right, so we will have the following situation. There is a system with its Hamiltonian, and it's in contact with a bath. So usually a system of large degrees of freedom, which is also with its own Hamiltonian, and the bath is at some thermal equilibrium state, okay? So here, when I talk about thermal equilibrium states, I'm talking about Gibbs states that for each Hamiltonian are defined like this. in terms of some inverse temperature parameter beta. So what we can do, so thermal states are given for free. This comes from the first law. Then from zero law. Then first law says energy must be conserved. So the operations that we are allowed to do in compliance with thermodynamics would be operations that conserve the energy. They have to conserve the total energy of our system and the environment. So what you're allowed to do is you start from system uncorrelated from an environment in a thermal state. You're allowed to do unitary operations, so reversible transformations, which conserve the total energy. And then, of course, you can only operate on your system. So you trace over the degrees of freedom of the environment. This overall operation here defines a channel on your system alone. Yeah, so this is a dilation of a channel. You do unitary energy preserving on system and environment. Then you trace over the environment. And this defines what is called a thermal operation on your system. Okay, so what we say in the resource theory of thermodynamics is thermal states are free states. Thermal operations like this are free operations. And now what we want to do, we want to extract work from quantum systems only by using free operations, which are the ones that by themselves cannot take a state out of thermal equilibrium. Okay, so if you're already out of thermal equilibrium, you can distill some work from your state. If you're at thermal equilibrium with this kind of framework, you can't get any useful juice out of it. Okay. How do we actually quantify the work we can extract? And this is a problematic area. I've already glimpsed at posters outside. There's even a poster that says there's many definitions of work and heat in thermodynamics. It's true. So we are taking, within this resource theoretic framework, the approach which is asymptotic. So the idea is we start from a system with some Hamiltonian and the bath, and we start from a certain number of copies of our battery. The battery is a simple two-level system with a Hamiltonian like this, so an energy gap E. And if it's in the ground state, it's empty. If it's in the first excited state, it's charged. So what we want to do, by means of, so we imagine that we have many copies of this initial system and battery, and we want to transform this into many copies of a charged battery. And we don't really care what happens to the system. We want to extract all the work, put it in the battery, by means only of thermal operations that preserve the energy of the total system. So we define the work in this asymptotic regime as the maximum rate of the number of batteries systems that we can charge by means of thermal operations in the limit in which we start with infinitely many copies of our system. This type of definition is familiar for entanglement theory. Say you use it also to quantify distillable entanglement, distillable coherence, something like this. Here we're looking at how many batteries we can charge in the limit in which we start from a lot of systems, okay? So what has been proven in these old papers now is that this quantity can be computed. So if you take the limit, this, which is what we call our work extractable from the state rho of the system, converges to the difference in free energy, which is effectively the relative entropy between my initial state and the thermal equilibrium state. So this now becomes a measure just of the athermality, so how distinguishable my system state is from being thermal. And this distinguishability quantifies the amount of work that we can extract asymptotically from our system by means of thermal operations. It's a very nice result. So whenever I'm going to talk about work extractable from a state, I'm going to just focus on this relative entropy quantity. What is also nice is that this, just for information, this resource theory is reversible. So if I want to consider the opposite process, sometimes in entanglement theory you call it dilution. Here you can call it, I don't know, you want to invest, spend the work that you have in your battery in order to create certain copies of your states. If you want to do this, so the work of creation, not the work of distillation, also converges in the asymptotic limit to the same quantity. So this is a quantity that tells you how much work you can extract from your state, and then how much work you need to spend to create back your state. Nice. Okay, and so the question starts to be, okay, so we have a measure. This is our main figure of merit for our thermodynamic tasks. And then you can start thinking about what features of quantum systems might be helpful in order to allow you to extract more work. I've been working on these areas on and off for a while. So we have previous results in which we identify different characteristics of quantum systems which allow us to extract more work in this kind of framework. It's funny, a couple of them were done with this Benjamin Morris, who's now a police officer. He changed his career completely. And when he saw my paper on archive with Guilherme, he sent me a text. I don't know, he's still following archive while interviewing criminals, but still following archive, sent me a text. I can see that the specter, the ghost of work extraction still haunts you somehow. Oh yeah, so I'm still working on this on and off. I keep getting people who like that. So what we did with Ben were a couple of case studies. For instance, in the first one here, we were just saying, if Alice and Bob are correlated, the goal is to concentrate as much work as possible on Bob's side, then Alice can help by doing some operations on her system, communicate results back to Bob, and this will allow Bob to extract even more work. So we made some quantitative connections between the additional work we could obtain that way, called work of collaboration or work of assistance, and the correlations in the initial bipartite state, classical and quantum, depending on the situation. The other work we did with him was also a bit more interesting because we were trying to make sense of this Gibbs paradox. So in classical thermodynamics, you might have a situation in which you are mixing two gases, and depending on whether you are able to distinguish these two species of gases or not, you will get zero or non-zero entropy production. And this was supposed to be a paradox, but actually Gibbs realized, and not Gibbs, but also Jaynes realized that it depends on how you actually quantify the ability of the observer. So if the observer has intelligence about these extra degrees of freedom, can extract more work in the classical system. If it's ignorant, or if you want blind to those degrees of freedom, they cannot extract any work. This is in the classical case. What we find in the quantum case is that actually ignorance is not a disability. So even if you have an observer that does not see the difference between two gases, they can extract as much work as the fully informed observer. And this can be interpreted starting from some basic phenomena which are already known in quantum optics. But that was surprising at the time. So it was a quantum version of Gibbs paradox. And so we had it a couple of years ago. So this is just examples to show that there are some quantum phenomena which somehow contribute to the resourcefulness of thermodynamics in the sense that they can enhance work extraction. On one hand, correlations, the other hand, resistance to ignorance, if you want. Of course, in this talk, we are going to focusing on non-Markovianity and its role in this problem. But to focus on non-Markovianity, we need to upgrade our description to dynamics. So far, we were just talking about how much we can do from states. Non-Markovianity characterizes evolutions, processes. So first step is we need to define the work extractable from channels, not just from states. Luckily enough, again, this has been done. So a few years ago, Miguel Navasquez and Cristina Pintus, they considered the following situation. You have a quantum channel. And what is the maximum work you can extract from the channel? It's a nice question because it really tells you how useful your, now not just the state, but your operation is for thermodynamic purposes. And what they found is that the best way to extract work from a channel is a simple protocol where you create an input. So you need to spend some work to create this input, and we know how to quantify this. And then you extract the work. Oh, this is supposed to be an arrow, but okay, it's fine. You extract the work back from the output. And the only thing you need to do is you need to maximize over the input that you create. So you will spend some amount, but maybe you can extract more work at the output. And so the work extractable, the net gain in work from a channel is maximum of the difference between the work extracted at the output minus the work cost of creating the input. Fine. And then it took a long and difficult proof to show that even in this dynamical level, the resource theory of thermodynamics is reversible. So if you want to spend some amount of work to implement this channel, the work cost converges again to this quantity. It's not always computable because this optimization is non-trivial. While, for instance, for states, we only had relative entropy. Okay, so it was just distinguishability from the thermal state. Here, you need to do an optimization over the inputs. Okay, nice. We are going to use this, but this is not the most general way of evolving quantum systems. So what quantum systems do, they evolve in time, and you can characterize this evolution in time in continuous time, if you like many of you do, with master equations and so on. But if you think of, say, conditional models or circuits describing how state of the system changes discretely at different time intervals, then we can adopt a more pragmatic perspective, which is the one of multi-time processes. So the idea is we have our system, and this system is in contact with some environment, and we don't know much about what's going on there. We can intervene on our system with some control operations that we can implement at given time intervals. Like here, we implement this at T1, we implement this at T2. In the meantime, the system is just interacting with this uncontrollable environment. So if we want to describe now the evolution of our system in terms of this process overall, the output state of the system is now described by a mapping, which goes from the input state and our control operations to the output state through something which is this P is called the process tensor. So this is an object which really maps system and control operations to the output. And it has this structure as a comb, yeah? Because the idea is that, why it's a comb? Because the idea is that you can have some correlations in time between previous, past, and future. What is done in the past will influence the future in general. So you already start to see why non-Markovianity enters in this description. That's nice. Of course, we can also take advantage of this situation to improve our ability of controlling the system at time intervals, because we might, for instance, consider also some ancilla, some side memory, do operations which also create and exploit correlations in time. So even the control mechanism is a comb. And the overall evolution in this discrete time theory, the most general way of describing an evolution is in terms of this interlocking of combs. Okay, so this is an area I've never worked on. So if you start having technical questions about combs, either ask a barber or Guilherme, right? That would be good because he knows a lot about it. But it's cool, it's nice. So the output system will be characterized by exactly this mapping here. Now, how can we bring back this description into something more familiar? We can equivalently decompose a process tensor, a comb, in terms of a sequence of quantum channels, but these quantum channels have memory, okay? So the idea is, at the beginning, there will be just, imagine each of these will be interactions with some environment, okay? So at the first step, system interacts with an environment, and this is a net effect of a channel on the system, P1. Then the next one, this is not defined a priori. This is a channel depending on what has happened in the past. So depending on what particular input comes here and mechanism happens here, this channel will change. And then here, there will be another channel conditional to what has happened in the whole history of the system. So general decomposition of process tensors is in terms of a time-ordered series of quantum channels with memory. And in this framework, we can understand a definition of Markovianity or non-Markovianity. When this is not the case, so when actually we can decompose the process tensors into a time series of channels which are independent of the past, then we say that this process is Markovian. Okay, so this is, we've heard lots of talks about non-Markovianity already. This definition is slightly different from the one based on the usual notion of CP divisibility. Actually, the two things are not equivalent. If a process is Markovian, as defined by process tensors, then this implies it's CP divisible. But there's even a paper, I think, by Modi's group, first author is Simon Mills. The title is something like CP divisibility that is not equivalent to Markovianity or does not imply Markovianity, something like this. So you can find instances of processes which are CP divisible, but which still have some multi-time correlation somehow. Still some memory effect in there, which prevent you from decomposing it in this way. So we will adopt this definition, which we find pragmatic, for a Markovian process. Anything which cannot be decomposed this way will have some non-Markovianity in a way or another. So now we are coming back to using resource theories, but we want to use resource theories not for states and operations, but we want to use resource theories at the level of process tensors, which is, let's say, 2 steps up the hierarchy, yeah? Because we have to classify process tensors as Markovian versus non-Markovian, where the Markovian ones will be the ones we might consider free, and we want to appreciate the value of the non-Markovian ones. And we need some quantifiers of non-Markovianity for the ones which are not of this form. And this is an interesting story, another one. So Cavan-Modis group, they defined this resource theory at the level of process tensors. They gave conditions for which quantifiers of non-Markovianity should be physically valid, so monotonic under certain particular transformations. They proposed some measures based on choice states, so dilation of process tensors into states, and they claimed these measures were satisfying their own criteria. Then Guilherme came along and they said, actually, it's not true. So he found mistakes in their work, and he defined the measure which now fixes all the problems. And he has published a single author paper, very nice, about it. It's been highlighted as editor's suggestion. So we have a measure of non-Markovianity which satisfies all the good criteria. It's very complicated to calculate. Why? Because the idea is, so we have these process tensors, we have our own control operations. We want to distinguish between the output coming from our process tensor, which might be non-Markovian, from the output coming from any possible Markovian process. So let's navigate the formula. This is our output. This is the output of any Markovian process for the same control block. And then you maximize this relative entropy here over all control blocks and minimize over all Markovian processes. So somehow you're looking, again, at a measure of distinguishability, but at the level of processes. But you have to go through the decomposition like this. You cannot just simply dilate the process into choice states because it doesn't work. So we will take this as a measure of non-Markovianity for our process tensor. So we have on one hand, background thermodynamics, measures of work for states and channels. On the other hand, we have process tensors, which are even more general. They are sequences of channels. And we have measures of non-Markovianity for this. Now, what we need to do is to relate the two. So we want to characterize non-Markovianity for its potential role as a resource for work extraction from general quantum processes. Now, of course, if you ask this question, this is not the first time we ask this question. Yeah? So lots of papers in the past, maybe 10, 15 years, had found some examples in which non-Markovianity, specifically CP non-divisibility, backflow of information, played some role in some thermodynamic advantages. We tried now to give a very general and rigorous result by connecting these two resource theories. And I think we possibly succeed. Right, so how do we do it? Well, first step is we need to define the work extractable from general processes. We have states, channels, now we need to define work extractable from processes. And here we found that there's not an obvious definition, so we came up with 4. And actually these 4, they are in a very nice hierarchical structure. And we could have just kept the strongest one. But we want to explore all the way along this hierarchy because this gives us a transparent way of appreciate how at every step some manifestation of non-Markovianity comes into play and gives us more work and more work and more work. So we define first four protocols for extracting work from general process tensors. We call sequential, joint, global, and comp at the end. And then we identify 3 manifestations of non-Markovianity, which somehow we realize they are responsible for upgrading the work extraction at every step. So investment of work, multi-time correlations, system-environment correlations. The idea in this is, as I will explain in a moment, that if your process tensors is Markovian, then all this hierarchy will collapse. So this second, third, and fourth protocol do not provide any extra advantage. And the best you can do is this sequential one. Okay, so if it's Markovian, they are all equivalent. You don't gain anything extra. If it's non-Markovian, clever manifestations of non-Markovianity give you more and more advantages as you proceed in your sophistication of the work extraction protocol. Okay, so let me explain these 4 things. First one is, so for all the examples, of course, definitions are general, but I think it's easiest to just give an example for 2-step processes. Okay, so simple comp, which looks like a bridge, we open it up, and then it's first, proper channel. Second one is a conditional channel, depending on what happened first. So first attempt at extracting work from this process is, okay, we just exploit whatever we already know about states and channels. So we say, we have the first, which is a proper channel. Let's calculate how much work we can extract from the first channel. We know we need to optimize the input and then extract work at the output and maximize the difference. Fine. Then after we've done this, this channel will be defined now because we have selected some input here. So we move on to the next step, and we do the same. Optimize independently this one for its own input, extract work. That's why it's called sequential. You do the first channel first, this define second channel, do it there, move on next, extract work from the next one. We are not exploiting any potential correlations which are happening across time. So in this case, the work you can extract this way is just the sum of independent work that you can extract from each of those channels, which have been defined in the sequence. That's the best you can do for Markovian processes. Why? Because for Markovian processes, even channel 2, 3, 4, all of them in the sequence, they are independent of the previous ones. So they are already well defined from the beginning. And so they have no correlations between each other in time. So you can just independently extract work from each of them, add this work up, and that's it. Okay? But if your process is non-Markovian, then you can do better. So first chance of doing better is keeping more or less the same structure, but thinking the following. So instead of extracting work after each channel, right? So I can still treat each channel independently, but I can make a plan at the beginning and optimize the sequence of all the inputs I have to send in so that at the end, the work that I obtain is the largest. This is slightly different from before. Before we were sending in and picking out. Here, we plan what is the best sequence of inputs, and then we extract work from each channel with this new optimized sequence of inputs. Okay, so here the work is now, if you consider this vector of all possible inputs over which you optimize, then you have the sum of independent work that you extract from all the channels, but you maximize a priori over the whole sequence of inputs. So why this might be better than before? Because we might, for instance, choose some row 1 here, which is not the actual optimal for the first channel. So we spend more work up front to send in some state that is not necessarily the best one for this single first channel, but which overall lets us extract more work at the final output. That's why we say this protocol improves over the previous one by simple use of investment, like you do in finance. Okay, so we invest more work at the beginning. Potentially, we might gain more at the end. Maybe it's riskier. If we just treat each individual thing sequentially, it's safer. But this one might allow us to do more. And what we do, at every step of the hierarchy, we want to connect the improvement to the non-Markovianity of the process. And we succeed by obtaining some, how do you say, continuity bounds. So if you define the advantage coming from this work investment, which is the difference of the work you can extract with this protocol minus the work from the previous sequential protocol, we can bound this from above by a function of some power of the non-Markovianity measure that Guillermo has introduced. That measure we cannot compute in general, but we can make some bounds. These bounds might not necessarily be tight, but what they tell us is, look, if our process has little non-Markovianity, then the advantage you can gain out of it is limited, quantitatively this way. Okay? And this is still not really taking advantage of the full structure of correlation. So what can we do better than this? We can do better than this. What is the problem here? Okay, we're optimizing all the inputs, but then we are extracting work independently from each channel. So we can fix this. So what we can do, we can again optimize all the inputs, but somehow we store the outputs at every step of the way, and then just focus on maximizing the work we get at the very end. So somehow we need to bring some side memory, make a plan. Do not just take out your gains from the investment at every step, but just wait until the end. And I mean, some of these things really financially make sense, yeah? So the final work that we get is just the work of the output state, where now we are characterizing this as just the comb which inputs all the sequence of inputs that we have defined before and stores all the results until the very end. So the work here is now the difference between the work of the final output state minus the cost of all the individual inputs that you have created, again, maximized over the sequence of states. This is better than before. in principle. It can be better than before. And we can look again at the difference. So now we look at the difference between this protocol and the joint one. And we find another very neat continuity bound. In this case, we don't have that weird power. The advantage coming from what is the mechanism here? The mechanism is the fact that non-Markovian processes have correlations in time. So instead of just cashing out every single time, we exploit these correlations in time to maximize the work at the end. So the multi-time correlations give us this improvement, which is directly bounded by the non-Markovianity of the process tensor here. That's very nice. I think this is, out of the four, this is the step I like the most. I think this already gives us almost everything. Can we do even better? Yes. Why? What can we do? I mean, the only other thing we can do is, here we're just considering optimizing inputs. So we are still talking about just sending states of the system through each channel. The only other freedom we have is we can come up with ancillas as well. So instead of just optimizing individual inputs, we will just have system and ancillas. And overall, if you want, this is just a dilation of a general comb. So the best thing you can do, you just come up with general comb here that might involve your system and some ancilla as well. And then you optimize over the cost of creating this comb versus what work you can extract from the output state at the end. Okay? This is a little bit subtle because you need to define the cost of creating this comb. We do define the cost of creating this comb by dilation. This might not be necessarily optimal, but I think this is the best we can do in our work so far. So the comb can be created by bringing an ancilla and doing a sequence of channels on system and ancilla. So the cost of implementing the gray comb would be cost of creating the ancilla, and we know how to characterize work cost of states, plus the sum of the cost of all the channels, and we know, and we know how to characterize the work cost of channels. So this one here is work cost of implementing the gray comb, and then you just maximize the output work that you obtain after you have done all this. And this can be strictly bigger than the previous one. And again, you do difference between this and the previous step. And what is the advantage here? It comes from the fact that you're bringing in an ancilla. So non-Markovian systems, you can have system and environment correlations which do not get destroyed after every single step. Okay, so we exploit the system environment correlations to enhance the work even more, again, by a factor which is proportional to this power of non-Markovianity. So if we bring it all together now, we have this hierarchy. We identify the three mechanisms, which only in non-Markovian processes give us more work every time. And you can compare now the Markovian case, this guy is Markov, right, with the non-Markovian case. So the best non-Markovian case is this comb protocol. The best case for all Markovian processes all collapse to sequential one. We have three levels of improvement which are coming from this mechanism. And overall, they're all bounded. The work extractable this way is all bounded by functions of non-Markovianity. So it might be that there's even further better protocols. I don't know. I think this is the best we came up with. If you are fans of Dragon Ball, this is the base form. And then we have Super Saiyan level 1, 2, and 3, non-Markovian protocols. Maybe you can go beyond. You know you can go beyond. But so far, I think we are happy with this. Now, I think I already had some free time. But in the paper, if you're looking for, I'm just claiming stuff, or these upper bounds are how loose they are. We have specific examples of very, very simple processes in which, for which this hierarchy is strict. Okay, so for instance, in the example A, joint is strictly better than sequential. In the example B, joint is useless, but global is giving you non-zero work. In example C, comb is strictly better than global. I can explain what they are, but maybe you're tired already. So they are described in the paper. The final, we don't need conclusions because I think the Dragon Ball picture is enough. So what can I say? I think we have proven in a very rigorous way that non-Markovianity for general multi-time processes is a fundamental thermodynamic resource. So it's a power up for quantum thermodynamics. And I'm happy with this, very happy with this. And I'm leaving you with the final slide, which is a little poem which was written 5 years ago after the second Quantum Information Thermo Conference in Brazil. So it's in Natal. I'm hoping we get new memories similar to this. I think this left-hand side would still apply to this week, definitely. Right-hand side is maybe a little bit more specific to Natal, but I really enjoyed it, and I hope that this series of conferences continues in Brazil. Thank you.
Questions?
Stop.
Hi, Gerardo. Thank you so much for the very interesting and nice talk. I was wondering in this formalism of the process tensor, which very nicely displays the effects of non-Markovianity, if this can shed some light into other, perhaps more exotic resource theories, like some non-convexity stuff, if you maybe rephrasing to this language could also give some improvements. If you thought about this or...
Oh, that's a very, so I've thought about, of course, that's a very nice question. Non-Markovianity by itself is non-convex. That's a good question. I've worked on these two things separately. So I've worked on non-convex resource theories at the level of states and operations, trying to make sense of what it means for classical mixing to not be free. And we have examples in which we understand this, even operationally. So every state which is outside of even a non-convex set can be useful for some application. This is something we have found out. I haven't looked at it from the process tensor point of view, but we want to, because, I mean, I have one student working on non-convex theories and then Guillermo working on this, and they have lunch and play board games every day. They really want to find something together. So we started this conversation, but thank you. I think it's possible.
All right, thank you.
Thank you, Gerardo, for the nice talk. Here,
yeah.
the very front. What are the restrictions you have to make in the comb P and the comb S to guarantee that you are satisfying the laws of the thermodynamics?
That's a good question. So I think the comb can be completely general, the green one. And so I think, so the point is we are using work extraction as our paradigm. So these processes can be completely general, but the ones which enter into the extraction of work, they need to basically involve sequences of thermal operations. So in the gray one, we have this. So we will decompose it as a sequence of channels which have to respect thermodynamics, and we extract work that way.
Hi, Gerardo. My question is, so I guess all of these kind of work measures for the different kind of steps, they usually involve optimizations, right?
Yes.
Is any one of them actually kind of feasible or manageable to calculate in practice, or are some of them kind of intractable in practice?
So they're usually hard, yeah, of course. For these simple examples, we could, but they are really, I mean, these are examples which involve swaps and simple stuff. And for this reason, all the bounds we have, they are upper bounds. We don't really have lower bounds. So it might be that non-Markovianity is there but doesn't help, but we have cases in which it definitely helps, and definitely not having it doesn't give you anything good. So they can be computed in simple cases. I think I told already Guillermo that we should work into maybe developing some numerical framework to evaluate these things, because otherwise we only have very contrived examples, just to show that these things actually have a strict hierarchy, but they do not necessarily represent physical processes.
We're going to have just one more question, and then I invite you to approach Gerardo at the end. But Saru, is a question.
So is it possible to write the process tensor as a matrix product operator? And because
it looks like, yeah,
it looks like
exactly one of the
tensor. Does it help, or is totally, you don't know?
I've not done calculations yet, but I have to check. I'm sure this must have been done, because this is, I mean, all the people coming from condensed matter, we have been using matrix product states and tensor networks for you have been using it for decades. So I think this is done. This is done. Kavan himself to calculate the Markovianity and to describe.
So just not to delay the presentation, let's thank Gerardo again. Move to the next.
Oi? É 25. Isso. I hope that doesn't fall when I... Boa. The pointer I just...
So next speaker is Krisia from IFISC.
Yes,
The floor is yours, Krisia.
Hi everyone, I'm super excited to be here. As many of you, it's my first time in Rio. It's such a shame that I'm from São Carlos, and at the time I was a PhD student there. I wasn't aware that this quantum thermodynamics conference was happening there. But as the title of my talk suggests, I will be talking about entanglement. And at the time I was a PhD student, I started to enter this field of quantum thermodynamics and also quantum information because of an entanglement. So the excuse that I had at the time that I was not aware of this conference is because I was very obsessed about the transport in the Kondo problem, and Caio explained a little bit about this during his talk. So I was extremely obsessed. But because of quantum info, I decided to adventure myself in entanglement. And one of the reasons why I started going into this field was because I wanted to use entanglement to characterize the size of the Kondo cloud at the time. So with years, now how do I pass this? Okay. O meio passa, okay. No. De baixo volta. So you already saw the spoiler of my presentation, but okay. So yeah, so at the time, as I told you, I was living in my condensed matter bubble, which is the side of the piston, right? And then I was introduced to this idea of entanglement. And nowadays I can tell you that I'm my own Maxwell demo, in the sense that sometimes I allow myself to interact with the condensed matter community. I take some nice ideas, then I go back to the quantum info community, I get some nice ideas, and then I'm in between both worlds. But this is my story on how I entered this field. But today the talk is going to be about what are the implications of entanglement and quantum materials, which are resources for you to activate some phases of matter, and how does it impact the thermodynamics? And to address this question, which was something that we started doing back in the day, we focus specifically on the work that you have to invest or the work that you can extract when you cross a phase transition. Okay, so this is the basic idea of what this talk is going to be, and I will show an example. So this is more or less the plan of my talk. So as we saw through all the presentations and the talk until now, we can say that correlations could be considered a resource for thermodynamics. And then a natural question that emerges is how much the level of entanglement that a given system has will affect the statistics of work, how much work you should invest, what are the work fluctuations that you have associated to a non-equilibrium process. And an example of a quantum phase transition that will be addressing this question is a very particular transition that has very interesting entanglement properties, which is the superfluid to insulator transition. And then with basically this toy model and other quantum phase transitions also modeled by Hamiltonians from condensed matter physics, we might answer a question is, does entanglement shapes the work statistics? How much work you can extract or invest in a system to activate some phase of your material? For instance, superconductivity, which is the current hunt in condensed matter. And then maybe this might help us to address, let's say, possible new phases of matter using thermodynamics. Okay, so as I already told you, and this is actually a slide that emphasizes how I started getting curious about this field, which was this nice work by Mika Day and other coworkers who are here in the audience, which makes this very intimidating for me. But we saw on Monday, right, this idea that you can cool qubit to a cooler state and heat a hot qubit to a hotter state if these two qubits are correlated. And I was a PhD student at the time. One of my best colleagues, Thiago Batalhão, was also involved in this type, in this work, and he was working at IFISC as well. Actually, he moved to IFISC from UFABC to work with Roberto Serra. And I saw this nice work, and a natural question then someone from a many-body community would ask is the following: what happens if I scale up the system to more qubits? And then this would have an impact, for instance, in the efficiency of heat engines, the efficiency of thermodynamical process. And then, as Anderson very well said, more is different, but is more different quantum thermodynamically? So this was my question at the time. And then, of course, you're a PhD student. You think, oh, I'm finding new things to do. But of course, you have to go to Google Scholar and ask, is this a naive idea or is it an authentic idea? How come nobody before me thought about this? And I went to the literature and I found very interesting results already about the effects of how the many-body effects in the work statistics. And by work statistics, I will emphasize again, I mean the average work that you have to invest and how much fluctuations this process will cost you. And I found a couple of interesting results, including this very old paper, if you think that nowadays we are in 2024, Alessandro Silva discussing the first and the second moment of the work statistics, the work distribution when you cross a quantum phase transition. But in this work, they were basically interested not only on the work itself, but how far from equilibrium you go when you do this as a sudden quench, an instantaneous change in an order parameter. So imagine the following. You could have something like a ferromagnetic phase of your material, and then you would like to bring it to a superconducting phase or a paramagnetic phase. You have to change some control parameter in this process. If you do this instantaneously, how much work does it cost, and how many fluctuations this is going to depict? So this was more or less the object that I started to become obsessed about it. And if you see my Google Scholar, you see that most of my works on quantum thermal are trying to investigate the work distribution. And I found these interesting results. And I asked myself a lot of questions that afterwards, a few of them were already answered. So what happens if I do this not as a sudden quench, but as a finite time? What happens depending on the control parameter that I use to go from one phase to another? How much entropy this process involves? And many, many other interesting questions. And another interesting result that I found in this process of digging the literature was the advantage of many-body effects in the efficiency of quantum heat engines. So we saw yesterday the quantacell, the celebrated quantacell. And so if you use many-body effects, your storage in a quantum battery will be enhanced. And the same for the efficiency of other engines or refrigerators. And I found this very interesting. But one of the things that I didn't see that I think has been overlooked in many of these studies about advantage of many-body effects is how the level of entanglement in these many-body phases would affect the efficiency or the efficiency of your process, or how much equilibrium, or how much it costs energetically. So this was more or less the questions that I have. And for some of you, maybe some of you saw nowadays, because from the early experiments carried out here at CBPF and also at Federal University of UFABC, there were experiments only dealing with a few qubits, 2 up to 4 qubits. Nowadays, a paper just from the past year implemented a quantum heat engine in a quantum cold atoms platform, and they showed this nice result that they address this cycle in which you can change the particle statistics to perform work. So you are crossing basically a Bose-Einstein condensate transition to a BCS phase, and they say like they're able to study what is the efficiency of this process in a many-body experiment. So this is very nice. And what is nice about these platforms, not only because now we can do quantum thermodynamics and many-body quantum thermodynamics in these platforms, is that they are also able to measure finite time observables and observables in time. At the same time, they can now address entanglement. And one of the issues about entanglement in many-body systems, as you know very well, if I want to characterize back in the day, old school condensate matter, I was one of these people. And what we used to characterize quantum phase transitions. So imagine this is the phase diagram of the extended Hubbard Hamiltonian. You can see many different phases. So SS is a singlet superconductivity. TS is the triplet superconductivity. It has also charge density waves, spin density waves. Back in the day, when you want to build this phase diagram in terms of observables, what are the observables that you look into? So magnetization, local charge, spin correlations, spin strings, which in the end of the day are measurements of entanglement. Why so? Well, we know that if you want to detect where a quantum phase is, you just have to find no analyticities of a given order parameter. And it turns out that the entanglement also shows a discontinuity when you cross a phase transition. So now, instead of looking into local observables, you can think about single-site linear entropy, local entanglement. If you want to measure superconductivity or superfluidity, you should be able to detect pairs. And for this, you can use the concurrence. So all these hierarchy of entanglement measurements somehow could be very useful for you to revisit these phase diagrams that back in the day used to detect different phases of matter and find new ways of characterizing the formation of quasi-particles which are responsible for these phases that we are interested when we are trying to develop new materials, for instance. And with that, now we go back and you can see so Yemini, who is here, was one of the first ones to revisit a phase diagram using entanglement. So there's a nice collection of interesting works to build phase diagrams using entanglement. So now we can ask, for instance, if I pick any point in this phase diagram and I want to quench my system, being instantaneously or at finite time, and I want to drive my system to a different phase, no matter if I have temperature, no matter if this external control field is time dependent, how much energy will that cost? So this is the question I want to answer on top of the question, how much entanglement should I invest in the system to generate this phase? Also, that's something I forgot to tell you, but you can also address what is the difference between quantum and classical correlations, and also you can measure, for instance, how much discord you have to invest in the system to activate this phase. Okay, so as I already told you, so this is the question I'm trying to answer here. So how much entanglement and how much work I should invest when I want to cross a phase transition, and how robust to temperature is this quantum phase transition, this thermodynamical process is. And on top of that, I can ask, does this hierarchy of entanglement measurements, I mean the single site entanglement, the concurrence, and so on and so forth, does it shape the work statistics? And I will show you that yes, and this was a nice collaboration with Irene D'Amico and Vivian França and Guilherme, who was a PhD student, who was studying a very specific type of transition, the superfluid to insulator transition. And he had amazing results characterizing this transition using entanglement. So we took advantage that he had these interesting results to address quantum thermodynamics in this kind of model. Okay, and we also touch these questions of what is the effects of temperature and what are the effects of the time-dependent dynamics. Okay, so how do we model the superfluid to insulator transition? With my favorite model Hamiltonian, which is the Hubbard Hamiltonian, but with an extra term, which is this point-like impurity disorders. Where is the pointer? Kind of. O primeiro? Fine. Okay, so you have this point-like impurities across your chain. So this is a picture. So why this model modeled superfluid to an insulator in transition? Well, the first term, which is the hopping Hamiltonian, it basically tells us that the particles are free to move along your material. Here I'm talking about a one-dimensional case. So this, you can picture this as a one-dimensional chain. So the hopping term does allow these electrons to move. This accounts for a metallic phase. If I want to add interactions and if I want to create superfluid pairs, I can basically add this another term, an attractive Coulomb repulsion, and this will glue particles of double occupied sites together. And if I have the impurities, of course, these impurities will suck electrons and spins to be singly occupied sites. So now to activate this phase transition, I have a competition of essentially 3 parameters. I can change the strength of my impurity potential. I can change the strength of the attraction, and I can even change the concentration of impurities. So these 3 ingredients are responsible for driving this transition in this model, this one-dimensional fermionic model. And what we know from the entanglement properties of this transition. So we know that if I increase the disorder strength to be strong enough, of course, my system will be essentially localized. So if I start from a superfluid phase, I can just increase this disorder strength and easily I will reach without too much strain, I will reach this insulating phase. I can also change the concentration of impurity. And as you see, if I have half of half of the sides of my chain filled with impurities, I will reach the lowest entanglement possible, and this signalizes a localized phase because, of course, I have only a single site. My wave function factorizes as a product state. So this tells me the signatures of this insulating phase. And of course, I can change the density. I will always see the same thing. So every time I'm at half filling, I will have the transition from the superfluid to the insulating phase, at least when I look to the single site entanglement. So single site entanglement is nice to detect insulating phases and localized phases as well. Now I can think about 2 possible protocols. In the first one, I can increase the disorder strength. So I can start with a V0 and go to VF, or I can add an extra impurity to my chain to drive this transition as we just saw before. So in each case, I can just consider all the possible ways of adding an impurity to my system and increasing the potentials. I have to average of all the possible impurities, impurity configurations, and with that, I will be able to see an average behavior that I will have in a material, because of course, in a cold atom platform, I can select where my impurities, but in a real material, I don't have this freedom in some platforms, right? So that's why I have to average of all of that. So this is the main object that we use it to characterize this transition thermodynamically, which is the work distribution. And I look into 3 moments. The first moment, the average work that I have to add to the system, or that I have to invest in the system, or I can extract from the system. The second one, the fluctuations of work. And the third one, the skewness, which measures essentially deviations from a Gaussian work distribution that in a few papers of ours we show that is associated with non-adiabatic effects. It kind of quantifies how far from equilibrium you are. Okay, and we show that for these two protocols, what a nice result is the following. The first moment is essentially proportional to the single site occupation. It tells you that the level of local entanglement dictates the first moment. The second moment, the fluctuations, are essentially associated with density functionals of charge-charge correlations. You can think about some sort of concurrence for charge, for densities. And the skewness is also associated now with fluctuations of 3-point density correlations. And this is more or less this story here. So let's take a look at the results. So this is the idea. Let's take a look at the results. What is nice about the fact that I have a function of the density here is that I can use density functional theory. Yes, it's a strongly correlated system. You will laugh off my face. But for the Hubbard Hamiltonian, you have a functional. You can use this amazing functional, and you can perform this calculation for very large system size. So let's take a look at the results. So first, ground states. This is an actual quantum phase transition. So if I look, this is a protocol in which I'm just quenching the number of, I'm adding an extra impurity in the quench protocol. And what I see, this is a plot of the entanglement for different strains of the external potential. And I see that when I reach the concentration, the critical concentration, I have minimal entanglement. I reach the insulating phase. Now, if I look at the work, what I see here is that I can achieve the maximum. Actually, this is the injection of work, not the extraction. But I can reach I have the maximum work that I would invest when I am at the criticality, when I am the critical point, right? So this is just the average energy that I have to add to my system to drive this transition. Let's take a look at the fluctuation. So here I show you the 3 moments. So this is something that we already saw before. This is the second moment. And what is interesting here is that because I have minimal entanglement, the second moment dictates the fluctuations is now associated with density correlations. I have minimal entanglement. That means I will minimize my fluctuations. And the skewness somehow captures the transition. It doesn't tell you too much, but it still have this feature popping up at the critical temperature. What if I increase the temperature? Sorry, as a function of the critical concentration. What about if I change the temperature? We know that if I add temperature to my system, my initial states will be more populated, and this will have quantum fluctuations competing against quantum fluctuations. So I will expect a lot of fluctuations of work. And in fact, this is what we see. But for intermediate temperature, so this is the ground state, this is an intermediate temperature, I see this increase in the fluctuations of work. The average work doesn't change very much, but the fluctuations definitely increase, but not that much. But if I increase the temperature to high temperatures, high enough, huge temperatures, of course, I have a lot of fluctuations. And now I don't have injected work. Now I can extract work from a high temperature initial state. This was for quenching the concentration of impurities. I can quench the disordering strength, and we see more or less the same behavior, but nothing that compares, if I think about the efficiency, the maximum work, is nothing compares, and the fluctuation, nothing compares with the first protocol that I just described. So nothing new here. Okay, so, and this brings me to the end of my talk. I know that it was fast. But I think the key message that I want to bring with this talk, okay, I just talked about the superfluid to the insulator transition, but now we have many models from condensate matter physics that we can explore, and we can address, for instance, how much efficient will be for me to go from a normal phase of a Hubbard Hamiltonian, this very beautiful model that models so many different quantum materials. How much work can I invest to drive my system? We have today this light-induced superconductivity. We have Fouquet engineered to allow us to peek into different phases of matter. So it will be nice for us to address this question of what thermodynamics can do to help us to build more efficient ways to reach phases that are not easily accessible for us experimentally. So, and sometimes, okay, I'm a theorist as well, as Dario pointed out. So with this curiosity that we have, we might answer some questions that are interested for people working in different fields. And I have a lot of questions that I still want to answer. If you want to understand better what happens when I just show you the quench, but you can ask me like what happens if I quench my system at finite time. I invite you to go to see Jeffter's poster. I have a lot of questions that I still want to answer. And now I have my students, which are my victims, because they will help me to answer these questions. And my final message is the following. Come to São Carlos, because we have very good people. I'm very proud of my colleagues there. And I can guarantee, because of course, I came from condensed matter physics, and Brazilians love condensed milk. And we have this nice dessert called brigadeiro. And I can guarantee that if you come visit us, I will prepare the nicest brigadeiros. Okay, so with that.
Thank you, Chris, for the very nice talk. And then we are open for questions now.
Thanks for the talk and amazing slides. Brigadeiro.
Yeah.
I'm not sure I understood how you compute the work distribution.
Okay, for the large, for 100 sidechain, I don't compute the work distribution. I get all the moments from observables that I can compute with the MRG.
But is it like the 2-point measurement schemes?
Yes, this is the scheme I'm considering.
And
yes.
wouldn't this destroy the entanglement? Like when you measure the energy basis?
I wouldn't say so, because imagine that I start from the ground state. I measure the ground state. I know that I'm in the ground state in the first point of the first projective measurement.
Okay, and so you...
Yeah, I collapse in a given state, which is entangled.
Which is entangled.
Yeah,
so
yeah.
it's entangled in the energy basis. Okay.
Yeah. And of course, if you do this at finite time, even if you start from a product state, you build entanglement in the system. So this is another question that you can ask. How the fluctuations that in the initial state are minimized because my initial state is not entangled at all, what is going to happen with that?
Thanks.
So I have a question concerning some reverse engineering. If you see a singularity of some sort in one of the moments, can you say that there is a phase transition associated or not?
Yeah, this is a question that I also have. What we saw is that at least this skewness seems to signalize the QPTs, at least the QPTs. Something that is very nice that just, this is a nice work by Giacomo Guarnieri. I don't know if you saw, but it was published, I think, a few months ago, and is a way for you to retrieve the work statistics from linear response functions. And this is nice because there are experiments like neutron scattering that you can just get these response functions for free. And I wonder if this could be a potential platform, for instance, to see if from these signatures and the moments you can say something about the phase transition. But it's a question that I also have.
More questions? No? Let's thank Crisia again.
Que vergonha.
Você segura comigo? Tá. Esse você coloca no seu bolso. Esse aqui é um clipe. Você coloca na lapela aqui. Na lapela. Alô? Tá esse troço aqui. Lightsaber para frente e para trás. Ok. So the next speaker is Thiago de Barba. So Thiago, the floor is yours.
Okay. Thanks to the organizer for letting me talk here in this awesome place that extremely important for the science of our country. And today I'll talk about the information broadcasting using finite resource. This resource in the meaning of the sense of the thermodynamic resource. I would describe what it is. And I also give some clue about ongoing projects related to the emergence of objectivity in this scenario. So first of all, what do we call by a thermodynamic process? Gerardo already told us about it before, but just let's revisit. We have some quantum process state that we have to prepare, or it could be like a thermal state. Then it passed through the process, and at the end we got another state that can be an out of equilibrium state, for example. And to do the process, we need some resource that can be time, energy, or your ability to gain information about the process. Yeah. Then I just took 3 examples here as for example, the preparation of this state or the preparation of I state can be a quantum thermodynamic process. Then we can see the process of do quantum operations or also do the measurements. The main resources we can consider in thermodynamic perspective are the energy we can store in a given quantum system, or we can plug the power cable in the electric energy. Also the time we have, but we need also a lot of control about the time to do the operations we are interested, and the complexity of the operations we want to do. Yeah, and also the complexity of the state we have to prepare to do some operation that we are interested. So the first question is, okay, it costs resource to prepare states, for instance, and the preparation of the states are important to do the operations we want. Then the first question is how much resource costs to prepare a pure state. Then we first have to take into account also the unattainability principle as presented by Gerard before. It's impossible to cool a system down to ability zero temperature with a finite amount of resource. It means that if you take like a Gibbs state and we want to convert it in a pure state, you have to cool this Gibbs state down to zero temperature, and it goes to infinity amount of resource. As for example, you can do the process using infinity energy in 1 step time, or for example, the Landauer erasing protocol, where you use infinity time and do the process at Landauer cost. That is the minimum amount of energy you can spend to do a process with a qubit. But also, you can also have to take into account the complexity you have to spend to do the process of purifying a quantum system. And we divide the complexity in 2 different complexities. One is the structure of the machine you are using to do the protocol. Yeah, you have to prepare the state of the system. You have to prepare an ancillary system. Then you do the interaction between both. Yeah, and the preparation of this ancillary system can be very costly by complexity. And you also must control the interaction that you are performing in the system with the machine. Yeah. Then this means, this means that every interaction that every process that you want to do, if you want to gain at the end a pure state or prepare a pure state in quantum thermodynamic regime, you need to spend an infinite amount of resource, and one of them can be the complexity of the controlling you are doing. This can be any process, like for instance, fine-tuning. If you do some fine-tuning in your system, change the energy levels of a given Hamiltonian, for example, you are controlling some process classically, and this can cost a lot. So let's discuss then if it's impossible to have, if we need to use infinity resource to prepare pure state. What you can do in a quantum information protocol if you are restricted to non-pure states, okay? So then we have this slide. The protocol I will talk is what we call information broadcasting. And let's consider Sonia represents the system, and Sonia is in real, and she has some amount of information, for instance, a picture of the word caipirinha, and she want to share with her friends. To do that, Sonia will store this information in a hard drive or a solid state drive, for example. And what the solid state drive will do would replicate, create redundant information to keep the information in order that observables, like, for example, to Sonia's friends, they can access the information. Then the information would be broadcasted to these two observers. Then the question is there any limitation imposed by the third law to create this redundant information, what we are calling information broadcasting? First is the first limitation we have is performed by the laws of the quantum physics, which say that the no-cloning theorem forbidding to broadcast the coherence of a no quantum state, which means that if the information that Sonia has some coherence out of diagonal terms and density matrix, it's impossible to broadcast this information. What can be done, it's only possible to copy the information encoded in the diagonal of the state, okay? Which means that in a given base, it's only possible to share the information that is encoded in the diagonal. But to do that perfectly, you need to prepare pure state in an ancillary pure state and do dilation, yeah? So a first kind of these systems or physical property that would allow Sonia to share the information, the classical informations, is what we call objectivity. It's pretty clear for us that caipirinha is an objective fact, and we can access it if we can spend some amount of resource like money to do that. So then consider then we have some classical information, and we have some memory, some system or observable, and we coarse grain these observables in many fractions, and you want to share this classical information with all those observables. If many observables can access the information independently and without creating any disturb in the original information of the system, we call it an objective fact. Like we do, for instance, when you send emails, yeah? Everybody can access the email without destroying the email we have previously. So one example in quantum physics is the objective fact is the state called the spectrum broadcasting structure. In every state that has this structure, a state without, in the system, there is no coherence. And in each part of the environment or the memory, these states are orthogonal one to other. Then it's always possible to share this information that is encoded in this diagonal without disturbing, because it's already diagonal. And they also can access the full information as they are orthogonal one each other. So then the question is, let's say then we want to share this information, then we can see there is a relation between what we call information broadcast with objectivity. Then the next question is, do the laws of thermodynamics impose limitations to objectivity? And the answer is yes. It's shown in this paper by Yelena, Nico, and Marcos that one cannot copy the information. You have information in the system. You cannot copy this information of the system to another system without disturbing the original information. Yeah. Then if Sonia wants to share the information of the caipirinha under the laws of the thermodynamics, even if it's to just one friend, she would lose some information that she has. So then the information broadcasting protocol is the following, yeah? So we encode information in a diagonal of the state of the system, it will be ideally broadcasting if all the elements of the memory, which means that all the observable, they can access by, there is a projective measurement they can access in their fraction of the memory, and they can, at the end, get all the information that the system had at the beginning, but we don't care about what is happening with the system at the end, yeah? Which means that I don't care if the information that I have at the beginning I want to share is destroyed, because if it's possible to do the broadcast, I always can make one more copy and take it to myself at the end. Then the objective fact is not is a more strong condition, because it says that I cannot interfere in the information of the system, but if I can neglect the interference of the system, I always could make another one to me. Yeah. Then let's say we have some state in the beginning. We prepare like a composed thermal state in the memory, and then we do unitary interaction. At the end, I have some state in the system, and by projective measurements in the memories, I would recover the information that is at the beginning. The problem is that what we found is this no-go theorem that says that it's impossible to broadcast the full information with more than a single observer. This means that even if we don't care about the information that is encoded in the system, it is impossible to share this information with more than a single observer. Yeah. Then in the case of Sonia, if she wanted to show the picture of her caipirinha, she will never can create redundant information. For example, the observers would get something else. She will try to share, for example, the word caipirinha, and they would get some pictures of some very beautiful capybaras. So which means that it implies that the thermodynamic, if you make limitations in the thermodynamic resource, the ability to create redundant information is forbidden. Yeah? We cannot create redundant information in this scenario. Actually, if you go to the paper and read the proof, it's only because in the beginning, if I don't erase the information that's in the memory, the more information I want to store that does not fit, because the entropy has an upper bound that's log the dimension. We also could discuss about the entropy production. This is the ugliest slide I'm going to show to you. Don't mind about. It's just that we found what we call Holevo-Landauer bound. That is a bound between the amount of information you can copy to each memory. Yeah, this is quantified by the Holevo information. And this is lower bounds the entropy production, which means that the entropy I produce in the memories will restrict the amount of information I can copy and I can access. Yeah. Then I cannot access the full information if I can copy it. So then some physics also in this perspective should emerge from these facts that I just showed. And if we consider this kind of coarse grain, when we take like the amount of observers, the amount of fraction of the memory is finite, but inside each fraction, they can be very, very large systems, like macroscopic systems. If I do this in this protocol, what I get at the end is that the information, the ideal information broadcast is achieved, which means that in the classical limit, if each memory is a macroscopic fraction of the memory, then I can broadcast the information and also without disturbing the system, which means that the objectivity emerges from this formalism in the classical limits, and this is in agreement with this paper by Gerardo and co-works. So let's say now that we relax the ideal broadcasting protocol. It's too strong. Objectivity is very strong. Ideal broadcasting is another strong idea. Let's relax this idea, and we only impose that the observers, they agree on each other, okay? They receive some information, they decide a protocol to do with Sonia, and at the end, they don't care about to receive the picture of the caipirinha. They are fine with beautiful capybaras, but they want to receive all the same capybaras. It's what more or less people are doing nowadays in WhatsApp. They receive a number of fake news, and they just care about agreeing with each other. So let's consider the following, then the protocol that's called biased joint information broadcast. This is related to the concept called intersubjectivity. When we, the process satisfies what we call a biased joint information broadcast because the information that everyone is receiving is biased, okay? Then I have some information and I have some observables. Yeah, they are observing the information, as you can see in the picture, and they can access locally the same information, which reproduce a noisy version of the information that was stored in the initial state of the system. For this, we define these two figures of merit that is called the agreement function. Then if we do nothing in the system and we do the same projective measurement in each memory, yeah, then we take the sum. This is the agreement. They would agree with the results that they will have. And we define another function that we call the bias. Then they will receive this information P tilde, and the information in the system is PS, represented by the vector with element PS. And then this D is simply the trace distance between these two probability vectors. Yeah? If this distance is 0, means that each observable is receiving exactly the information that is encoded in the system. And if they agree, the agreement information goes to 1. Okay? So what we found, we defined this function AX that is a function related to the thermal state in each subsystem of the observers. Like for each of these observers, they have some temperature, finite temperature. And what we found is that the agreement function does not depend on the information that is stored in the system, but depends only on the preparation of the memory. What is also interesting that if any of these AX goes to 1, the agreement is also 1. Then all the observers, they would agree on each other if one of these fractions go to 1, okay? Then, which means that if I have, say I can prepare a state in the observers that has rank equals to the dimension of each, of the state in each observers, if the rank of them is the total dimension of each observers over the dimension of the system, then we can find perfect agreement. We don't need like a pure state at the end, but it must be pure enough, okay? So the bias is also bounded by the agreement function. It's like we call disagreement, 1 minus the agreement, times this, the distance by the initial information with this crazy probability vector, okay? So the important information in the slides that the agreement depends only the preparation of the local memories, and the bias depends on the agreement. If the agreement goes to 1, the bias goes to 0. Yeah. This comes from the symmetry that we can have between the memory and the quantum systems. When the agreement goes to 1, they cannot have any bias, which means that they cannot do what our friends are doing in the WhatsApp. They cannot agree on each other, can agree on each other with a fake information. If they agree on each other, the information has no bias. So also, it's interesting that we can improve the agreement without changing the temperature of the system, just doing coarse grain over the memories. For example, we have a memory, global memory prepared like in this composed system. If we do different coarse grains, like bigger or smaller coarse grain, we can go closer to agreement equal to 1. And this goes closer to 1 exponentially fast with the dimension of each local memory. Okay, so this is a proof for if the information has, if the system has dimension 2, and we try to do for a general dimension in general, but it is a crazy probabilistic problem. Then we did some numerics, and we see that this is the log function, and this fits very good what is a exponential decreasing in the disagreement function when we increase the size of the local memories, okay? Then they agree more if they have more elements. This is more or less related to what we have in our SSD drive, because the total capacity of the SSD drive is finite, like 1 gigabyte, for example, or 100 of gigabytes. But locally, they have amount space in your memory such that you can create redundancies inside that. Yeah. Then you need to coarse grain the memory in a way that the information should fit there. So that's it. The take-home message will be the thermodynamics in quantum mechanics context always create limitation for the quantum information protocols, including our ability to share classical information encoded in quantum systems. Also, the information can only be shared with, at the most, a single observer. This is the fundamental limitation that the protocol, the thermodynamics do in this kind of protocol. Ideal information broadcast can be recovered in the classical limit, allowing objectivity to emerge, and even intersubjective is not allowed by thermodynamics. Moreover, one can maximize the agreement that the observers can make together, and this would upper bound the bias that they can have in the information they can access. Okay, so the maximum agreement depends only on the preparation of the state. Then if you want to share information, you have to spend all the resources you have to prepare the memories, yeah, as the most pure memories you can have. So, but if you cannot prepare very good memories, you must do some coarse grains in the memory components, which means that you have to reduce the number of observers that will receive the information for a fixed size of the memory. So just have to say thank you also to my collaborators, that is Marco Zuber and Nikolai Fries, for this broadcasting paper. Also, the intersubjective, I'm working together with Felix Binder and Alessandro Candeloro from Dublin, and I hope this will be archived before Christmas. So thank you, and just remember that in Portuguese, militar is a verb, okay?
Thank you, Thiago, for the very nice talk, and start the question. Thank you very much. Can you bring back the conclusion? Yeah, thanks a lot. So what I remember from quantum Darwinism, things like Brandao and so on. So effectively, the idea is that you can, if you have many observers correlated with the quantum system, then effectively you can share the classical part of correlations, but you cannot share the quantum one. So I just want to understand. So this means that thermodynamics also gives you limitations in how you share the classical part, and you can only effectively do it when you have infinitely many observers or they're large. Is this what you?
Yes. If the number of observers is infinity, you also have to take each fraction also go to infinity. In this scenario is slightly different from what we see most in the Darwinism context, because there we don't care so much about the preparation of the state of the observers. Then if they are all of them prepared in pure state, you always can do a CNOT gate and copy the full information. Then what people do in the Darwinian context, you have like open systems, you have some information in the system and coupled to an environment, and you want to see how the information is spread in this with all the environments. These are slightly different concepts because we care a lot about the preparation of the memories.
Okay. That's very good. Thank you very much.
Super interesting talk. So I wonder if this limitation of the information can only be shared with at most a single observer could be turned into an advantage in a cryptographic scenario, especially if you talk about this O-level Landauer bound. That sounds very interesting.
I don't know.
Okay.
Because
in cryptography, that's exactly what we want
exactly,
to do.
Because if the information is, the system is at the beginning diagonal in the base, yeah, this can be advanced, but it won't play much if someone, if eavesdrop just can intercept the message, because then at the end, what the receiver would get is some bias information. Probably they have to communicate, but I don't know. I think entanglement is much better, but we could somehow formalize like a finite resource version of this based in this idea. But my problem is that if you don't know the information that you are sharing, it's impossible to the sender and the receiver to agree with what was done before. Then I don't know. It's something that we should think about.
Maybe we can discuss later.
Yeah, it's nice. Thank you.
Hey, thank you for the very nice talk. I actually have two quick questions. The first one is when you're talking about agreement, did you think about this also from the perspective of parameter estimation? Like agreement also means that, each observer has to build an estimator and that estimator itself has to agree.
No, I didn't play with parameter estimation or thermometry yet. I know that there are some works in direction. For instance, Felix has a paper based in this direction for a finite resource measurement, non-ideal measurement with thermometry. But I didn't go in this direction yet. Yeah.
And then maybe if I can, quick second question, can you go back to the whole level Landauer bound that you showed? Do you have any intuition or anything interesting to say about what happens at zero temperature or in the limit that T goes to zero?
What happens in the zero temperature? It's a good question. I don't know. Because I cannot see, because, yes. Yeah, this goes to zero, this goes to infinity, yes. The interproduct would diverge.
Sorry, does that mean that essentially the whole level information is less important at lower temperatures?
When you have, yeah, good, thank you. Nice.
Fine. So I love the results and I have many, many, many questions, but let me just ask you one. So I think that many of the statements that you derived depend on the very specific choice that you make for the initial state, namely that you have spectrum broadcasting structure. What I was wondering is to what extent some of these strict statements can be loosened if you allowed for a little bit of fuzziness in the initial state. So let's assume that the environment, or let's say the universe, is prepared in a state that is within an epsilon ball around some single branching state. Then in that case, you should allow for a little bit of information leakage into all of these different fragments, which means you should be able to accumulate enough information at the observers to eventually learn sufficient information to agree. Am I correct or am I totally wrong?
Yeah, I understand the protocols say. Actually, the main result, for example, this is dependent on the fact that the initial state is a Gibbs state, but the main result is not. What the main result says that if the memory can be prepared in any mixed state, but if there is, but the number of the zero eigenvalues you have is important. And if you prepare the memory in any state that is a full rank state, the same applies. The difference is here, when we do the interaction between the system and the memory, we wanted to maximize the statistical correlations between the system and each component of the memory. And this depends on the highest eigenvalues of the memory. Then if I have any state, which means that if the state is passive, it's easier to track where the biggest eigenvalues are. Then if it is any state, then this concept of maximize the statistical correlations is slightly different. Then in the case you said probably, I don't know for sure, but probably you need like a smooth version of these quantities that when you play the limit, when this smoothness going to zero, you recover this kind of things. This is what I expect, yeah. Cool, thank you.
Thank you, Thiago. I'm going to ask a very naive and possibly stupid question. Okay? I mean, we can all read entropy production on the screen. So we are all receiving that information and assumingly perfectly.
Yep.
So in what sense are you saying that we are not actually receiving it perfectly? Is it because there are like tiny, tiny exponentially small fluctuations that we are actually not receiving it? We are only receiving part of what's on the screen? What is your sense that the information is not being classically broadcast?
This is a very, very nice question, in the sense that if we take into account the size of the things that we have in the classical world, for example, if I plug my laser machine in the 100 volts, it's, if you compare to h bar omega, that's the energy of a system like a qubit, it is infinity to that. It's already very, very, very large. In the sense that if you read like entropy production in your brain, it's available space to get not only this information, but all the papers that are in archive for the whole history. Then it more or less would be like you have your memory is like a density matrix with a lot of zeros, and all the information that is stored there already is very, very tiny. Yeah. Then this is why in the classical world it's possible to us to share emails and information, and I'm speaking words that everybody is receiving this information. But if you are in a day that your brain is very full of things and you are worried about stuff, you didn't sleep well, you have to reset the memory to read a paper in the morning in the archive. No? Then it's more or less, if there is enough things in your brain, it's hard to store more information inside. This is more or less the same thing, yeah? I'm not playing with quantum consciousness, is not this kind of thing. So, sorry, it's just trying to use the example you did to answer the question. Then in the quantum world, we know that the whole level information quantifies the amount of information you can store in a system, and the maximum value is the log of the dimension. Then if there's a lot of information already there, it's hard to put more information. It's the example I make is if you take a blackboard full of stuff written already there, and you wanted to teach a class without erasing the board, people will not understand the message. They understand something else. That's the example. Yeah, you have to reset or reset goodly enough to do that.
Okay, so I'm taking advantage of the fact that I'm sitting right next to Danielle and took the microphone for myself. Because I'm going to follow his question and your explanation at this point, because you see, your explanation was entirely classical.
Yep.
So, and that's something that it intrigued me during your talk, because you were talking about the diagonal elements and only the diagonal elements. So, I mean, I got the feeling that you are dealing actually with classical information the whole time. And actually your explanation to Danielle was classical, and it only dealt with classical information.
Yep.
In which case, usually we say that Shannon is enough to take care of everything that's happening.
Yep.
So then my question is,
What's quantum?
how do you relate to Shannon, if it's the case, or if not, what is the difference, or something like that?
Yeah, this is a very nice question. The point is that we know that the laws of the thermodynamics in the classical world, they allow us to broadcast information. Yeah, in the sense that even if I follow all the laws of thermodynamics, in this scenario, if I take the size of the memories big enough, like more close to something that is classical, then I recover something that's like a SBS when I can broadcast the whole information. I think that the main difference is that the laws of the thermodynamics do not impose limitation in the classical limit to us to share information. Of course, we can, our feelings can be sensible to the laws of thermodynamics, for example, if the environment is too noisy or too hot or so. But this is our we are sensitive to this kind of things. I don't see that, for instance, a SSD drive would not allow to create redundant copies, even if it's at room temperature. In this sense, it's quite different, yeah? Because of course, the SD drive, it's sensible to temperature, but this is more or less the difference, because in the quantum context, like, we have limitations in our capacity even to share classical information.
Okay, I'm not a computer scientist, but I think that you should be slightly careful when you give this type of analogy, because actually error correction becomes more and more difficult, even for classical computers, if temperature starts to go up, for example, or fluctuations in general, they start to go up. Redundancy has to build up. You need to, so there is a balance of resources there, even classical ones, with the amount of noise that you have in your system, and so that becomes really important, to the point that you need to put everything inside a refrigerated room and things. I mean, so anyway, I'm not a computer science, so I won't go that much into this, but like, I would say that to build up your analogy and to eventually separate classical from quantum, there might be something.
Yeah, there are a lot of things. I more or less go in the direction of the question you two asked. But yeah, we could like find other difference, and one of them is the amount of information it can store in the system is different from the amount of information it can access from the system. This is also something that we discussed. And this is related to the fact that this ensemble of this state can be not orthogonal. And I'm also not a computer scientist, and I'm not trying to convince you anything that I didn't do. What I'm just trying to say is that in this scenario, even if the systems are smaller, not classical, there are some quantum mechanics and also quantum thermodynamics limitations. That's the claim.
Any more questions? No? So let's thank Thiago and all the speakers of the session.
Thank you.
Well, we just finished the workshop today. We're gonna have the poster section outside of the building, turning to the right, and please enjoy and ask questions for the people there. See you tomorrow morning.